Good morning, good afternoon, good evening. Welcome back to Flat Earth School, the school that is around us 24/7 since the beginning of existence. This stream today is a Friday special edition of members only in the chat here watching it live. Thank you guys, whoever has the link here. I've got 14 beautiful patrons. We've got a couple in the chat. Hey, Michael. Michael is here early as always, the first one here. Thanks, Michael. Thanks to all my patrons. I really appreciate it. And without any further ado, let's get into this. So we've got Zach, Good Times for All. Hey, Zach, how are you, mate? Unmuted now.
No, you're muted, Zach.
Oh, I had both of them muted. Sorry about that.
All good.
Yeah.
Everybody does that.
Yeah, thanks so much for having me here, Mitchell. Great to be here.
Great to talk to you, Zach. And also Bob Knodel. How are you, Bob?
I'm doing just fine. Hi, guys. I'm not going to be on camera for long because, you know, I have a face for radio, not for video. So, yeah, just thought I'd pop out and say hello to everybody, and glad you're here for this.
Fantastic. So the premise to this argument today is all to do with the downward bias. This is a globe exclusive argument. This is some of the arguments that we need to have in Flat Earth here, because we've got past the globe, we've got past gravity. We don't need those things. The globe is non-existent. It's been proven not to exist. The Flat Earth has been proven measurable, navigatable, as I showed in my last few videos. So now these are advanced conversations that I want to start having with people about the actual nature of our reality, things that we can prove, things that we see, things just all around us. And that's what my videos are about. So we're going to be talking about a downward bias, whether there is or is not. And more specifically, it's going to be, what do you guys call it? The electrostatic downward vector? Is that what we're going to be calling it?
Well, yeah, electrostatic acceleration, if you want. Okay. That's like,
yeah, we haven't really picked an official name for it yet, because obviously the mainstream does not see things the way that we do, with the exception, of course, of the electric universe. The guys over at Thunderbolts Project, you know, Wal Thornhill and Don Scott and all those guys, I'm sure you're probably familiar with their work. They absolutely feel that this gravitational phenomenon, whatever is causing it, is electrical. And we feel very much the same way. And of course, Ken Wheeler dictates the very same thing. He calls it a modality of the ether, and we'll get into what that means.
All right, cool. So where do you guys want to start?
Okay. Well, go ahead, Zach.
Yeah, I'd like to start off by saying this isn't something that we came up with. This is, like, when I started looking into the downward bias in electricity, I found Walter Lewin, and he is a 4-decade MIT physics professor. If you don't know what MIT is, that's Maryland Institute of Technology. It's a very prestigious school. Or Massachusetts. Yeah, very prestigious school here in the United States.
Absolutely.
A lot of new technologies and stuff have come out of this place. So I figured I'd go there and see what that teacher is teaching his students that are, you know, creating these things. And I mean, Walter Lewin himself even says that gravity, the whole idea of gravity, does not take place until you're talking about like a moon going around a planet. Sorry, I got a lawnmower behind me. I'm going to close this window. A planet
it wasn't even coming through. All good.
Orbiting a sun, or, you know, that sun orbiting the center of its galaxy. Gravity is not something that takes place until you have electrically neutral objects. That's the definition of physics gravity today. You can go look it up at Caltech, at Harvard, at MIT. These are electrically neutral bodies they're talking about. So there is no connection between them. There's a vacuum, they're saying. Whereas, and we'll show you a video, he even says that, you know, here on Earth, even your own body, everything is dominated by these electric forces. And this is what's causing a downward bias towards Earth.
Yep.
Okay,
so that's how they, that's how they actually teach it at MIT.
Okay, so is that from the globe paradigm, or does it not have to be a globe?
No, that is from the globe. And he makes, it's a shame. He was a great teacher, but I think he was teaching a little too much truth. Like, he would point out the issues that science, I guess, the body of science has gone through with this. Maxwell changed some of the laws of electricity to compensate for the globe. You know, he said that the ionosphere can just magically appear above our heads in free space from the sun, which is, you know, that far away through a vacuum. That's impossible. It's never been done in experimentation, and it actually went against Maxwell's first equation. And he points this out in his class. You know, he was trying to teach his students where to look.
Right. They had to, and the reason he had to do that, Mitchell, was because when Faraday and Faraday came out and first did these initial broadcasts, they were broadcasting way too far, hundreds, thousands of miles, right? So they had to come up with a reason. Then all of a sudden the ionosphere was invented. And then they said, so what happens is the radio antenna broadcast, and it goes up, it hits the ionosphere, which is this charged area of the atmosphere, and then it bounces down, and then it comes and hits on the ground, right? Well, that should have been a big red flag for me a long time ago as a ham radio operator, because all signals, electrical, electromagnetic, everything, want to return to ground. They don't bounce off of ground, they return to ground. But yet the theory goes that it bounces off the ionosphere, comes down, bounces off the ground, goes back up, bounces off the ionosphere. And that way you can literally go, you know, multiple hops around the world. And they had to do that, but it was completely ad lib, you know. To
this day, there is still no scientific experiment or test even just to recreate this phenomena in a lab. They can't take a vacuum chamber, put in a positive, put in a negative, and have, you know, the negative build this ionosphere of positive charge around it. They can't do that. Right. They can create a plasma, you know, that connects the two when it gets strong enough of a potential to actually create a plasma charge, but they can't get that, what they're claiming is happening to our Earth. So yeah, in the globe model, this is how they say it works, but they had to fabricate the actual physics of our Earth and how electricity actually works.
That's really interesting, because I went live last night. Don't know if you guys caught it. It was Simon Dan. He just put a video out, and probably an hour before that, he was detailing the ionosphere in, well, it was really an argument against one of Taboo Conspiracy's awesome videos about just that thing, about being able to broadcast signals too far. And he brought up the ionosphere. It is something they absolutely need. It's something they absolutely don't have. And I brought up the point that if you've got any sort of atmosphere, you absolutely need a container. And unwittingly, they invoke containers left, right, and center. But I digress. To this argument, so this downward bias that we're going to be talking about is, are we going to be going through scientific principles, or are they more natural laws?
These are strictly natural laws. For the simple fact that we cannot get outside of this electric field that we live in to test it properly scientifically. You know, we can't remove that variable. We can alter it in between a couple plates or something like that and change the field within something, but we can never fully remove ourselves from this field to test it properly.
Okay, so the assertion is that the electric field is around us all the time, and we can't isolate ourselves from it.
That's true. And that assertion is backed up by mainstream physics. Mainstream physics tells us that we have an electrostatic gradient relating to 100 volts per meter that's been allegedly measured all the way up to 50 kilometers. I personally believe it goes to 100 kilometers because that's that magical 62-mile mark where I believe the lower limit of the firmament is. Now, obviously, and that's amazing that they say that, right? Because again, they're building this, you know, based on an ionosphere or something that's charged up there. But I find it amazing that, you know, they can say all this stuff is up there when even to have a charged area, you have to have particulate matter, right? And I'm not saying that there isn't any particulate matter up there, but the higher you go, the less matter there would be, right? Until theoretically you get into space and get into a 10 to the negative 17 torr, which is virtually no matter at all, right? So without particulate matter in the medium, an electrostatic charge is impossible, okay? So we have, and not only that, what's amazing about this is you're right. They claim that there has to be containment. Their containment is, of course, gravity. Our containment is a firmament, right? But at least we have evidence that shows this firmament is there. And of course, we've talked about that on several shows, so we're not going to go there today. But
no, this argument's definitely not about the firmament. We are definitely contained, whether it's a firmament or a non-physical thing, whether there's something outside the firmament. That's not a topic for this discussion. But okay, let's go back to the electrostatic charge. How do we know it's there? How can we measure it? How can we observe it?
Okay, well, yeah, you can get an EF meter. We have one here. Bob has one. Actually, let's do a little live showing of this. Yeah.
This is actually, have you heard of, well, I've got a video on that too. Mitchell will also be showing you a video where there are guys that actually are collecting electrostatic energy from the atmosphere. And here it is right here. I'll get it queued up to play. And after Zach demonstrates this.
Well, go ahead, Bobo. Do that one. I'm going to actually get some boiling water too to show how we can show that it's measuring this electric potential in the air.
Oh, okay.
That would be a great idea.
Right on.
Yeah.
You're going to see. You're going to get a big old demonstration here.
Live demonstration. That's what I'm all about here at Flat Earth School. Live demonstrations.
All right, cool. So let's look at this.
Stream. All right, we've got you up on screen.
All right, and ready? Here we go.
All right, this is a pole which is used for holding up the ion collectors high up in the air, about 130 feet or so. And then this is the drop line coming down from the ion collectors and going into the research shack. Goes through that PVC pipe and into the building here. Then the drop line feeds through my flip-flop limiter circuit, which feeds and charges up these 10 big capacitors.
Okay, so he's saying the storage capacity here is 33,000 joules. That is a lot of energy. Okay, and you know, this is, like I said, this is not uncommon at all. In fact, if you just Google or go on YouTube and search for ionospheric electricity harvesting, you'll find hundreds of videos, hundreds of people doing this. Now, the biggest thing that most people will tell you about this, Mitchell, is that they are not able to capture a significant enough of it to like run a city or anything like that. Now, that's what they say now, but there's significant evidence, you know, from our past that, you know, we already were harvesting this energy, and this has to do with cymatic resonance. But again, we're kind of, you know, deflecting from the point there. The point is that this electricity is there. And it's funny because the first time I ever discovered it was I was working on a tower, right? I used to build microwave sites. I'm also a ham radio operator. I was up on a tower at about 150 feet high. And what I did was I came across a ground connection that was running down to earth ground, and I touched it and I got shocked big time. I mean, a huge shock. And so, you know, obviously, you know, I knew at that time that it was static electricity, but I didn't think a whole lot from it. Didn't kill me because there, even though the voltage is high, the current delivering capability is very low. Okay. So anyway, so what they have is we have this 100 volts per meter, which has a capacity, really, if you go to the firmament, of 10 million volts, which of course, then you're talking in the zones of lightning strikes and things like that. So, and they tell us basically that this electricity is caused by, you know, air currents, warm air and cold air currents running by each other and generating an electric field, yada, yada, yada. I don't buy that for 1 second. The only way that you can be within a graduating electrostatic field is to be, like, for example, in between two plates of a capacitor. And that is exactly what I'm saying that we are in. The earth behaves as the cathode. and the firmament behaves as the anode. And in between the cathode and the anode, these two plates of the capacitor, we have, in fact, a graduated electrostatic field. And what he's doing is he's picking it up. This is probably no more than from 150 feet on the ground. So if it's 100 volts per meter, then, he's probably picking up 4,000 or 5,000 volts here, something like that, right? Enough you can see the arcing, and you can actually charge up these capacitors to 33,000 joules, which is a lot of energy. And let me play just a couple more minutes of this, and then we'll stop.
Being provided by the capacitors, which were charged up by ions from the air. They're being fed through a 2 meg resistor. Now we go over here and take a look at the voltage on our meter. This is 1,000 times probe. We're at about, 12 kilovolts. Yeah.
12,000 volts.
Over 12 kilovolts right now.
Right out of the air, Mitchell. Right out of the air. And that's only from, and now granted that's stepped up, but the idea here is to harvest it. So what you want to do is you want to be able to have enough storage capacity to do work in like power in watts. Okay. So power in watts is calculated basically by taking the current measured in amperes times the voltage measured in volts gives you the power measured in watts. So if I have 120 volts and I have 10 amps, that tells me that I'm generating 1,200 watts or drawing 1,200 watts worth of power, which will run like a hair dryer, right? A typical hair dryer. So just to give you an idea of the scale that we're working with here, and of course you can step that up and down. Go ahead.
Can I just ask, what are we looking at here? These capacitors, are they?
These are capacitors, yes. These are essentially what they are inside is what I have described the Earth to be, is they are layers of plates that are separated by a dielectric, and the dielectric can be anything from air to non-conductive type of material. Could be oh geez, what am I trying to think of? Like wax paper.
Wax paper, rubber, depending on how much electricity is going through there. It determines like those little cylinders you'll find if you ever took apart your electronics as a young child. The little cylinder that looks like a grain silo. That's a capacitor. It's just two pieces of thin metal all rolled up in there. And one side gets positive, the other one negative, and it stores that resistance, that static electricity. Charge. Yeah, the electrical charge.
And of course, the higher the voltage it is, the stronger the dielectric material has to be, because otherwise it will arc through and it will discharge itself. So you don't want that to happen. So there's a lot of variables in how they work, but
there's some interesting words. It just reminded me of the first time I heard about this kind of what you're calling it now, the electrostatic downward vector. The first time I heard of the argument was a couple of years ago, and I think you guys referred to it as the incoherent dielectric acceleration. Is that still something?
It's the same thing.
Same thing, yeah. Just that was like the scientific term I tried to put on it. The trying to add all the stuff in that actually takes account in that vector creation. Yeah, because it is pretty much electrostatic. That gradient that we have here is what causes it.
Yeah, that's a great demonstration. You can absolutely harvest electricity from our world around us. I think that's what Tesla was trying to do. That's a great demonstration. I'm just curious, is there any other way than this apparatus that you've shown? Is there any way, kind of just in nature, without a man-made apparatus, that we can demonstrate the static electricity in the air?
Well, yeah, lightning. That's all lightning is the electrostatics getting to 3 million volts per meter.
Or the
electric potential, the potential between 2 points, like the cloud and the ground, has gotten so strong. Like during a thunderstorm, it's not 100 volts per meter. It can go up to 10,000, 18,000 volts per meter. That's why you'll see some people standing on top of a mountain during a thunderstorm and their hair starts standing up, you know, all over their body, and they can stick their fingers up in the air and lightning will come off the tips of their fingers.
Yeah.
Yeah, that's crazy.
Here's the interesting part, Mitchell, is that, yeah, not only does lightning demonstrate it, it demonstrates that potential from the clouds down to the ground, right? And all that's happening there is the charge buildup between the clouds and the ground, or an earth ground, becomes greater than the resistance in the air can withstand, right? So you have what's called a dielectric breakdown. And when the dielectric breakdown happens, the discharge happens. And you get a current flow through the air itself. Now, the other way that it happens are called sprites and elves. And I don't know if you're familiar with sprites and elves, but they're essentially lightning discharges that go upwards. But the interesting thing about elves is that when they discharge upwards, they do something very, very strange. And that is when they get to an elevation, get this, of 62 miles, they flatten out like they're running into something, right? Mind-blowing stuff, right?
Really interesting. Yeah, really interesting. I think you went over on the last Globebusters episode about the sodium layer at about 62 miles too. That's that kind of number that keeps coming up. How do we know it's
everywhere?
How do we know it's 62 miles? I'm just curious. I didn't ask on the last episode.
I honestly can't tell you, other than, you know, when you watch the demonstrations of the scientists on the airplane, obviously they've got altimeters locked on it. You can calculate it, you know, for one way, or you could probably do it with some sort of internal small radar. But, you know, it shouldn't be a difficult thing to measure the altitude up to 62 miles.
Yeah, cool.
You know, that's
so
simple tech.
So you were detailing lightning going up and down. Why would we see it going in both directions? Is it like a change in polarity? Why do you think that happens?
Yeah, exactly. It depends strictly on whether or not the cloud is positively charged or negatively charged. If the cloud is negatively charged, through induction, it creates a positive charge on the ground beneath it. It grabs all the positive energy around and puts it into the ground right there to try to equal out that balance.
Yeah. Now, here's something that's just a little factoid here, Mitchell. You're going to like this. This is a widely reported phenomenon, but when people experience strikes of lightning that are very, very close by, you will very often hear something that accompanies that right before the lightning strike happens, is that things will start levitating off of the ground.
Have you got any demonstrations of this?
I didn't pop that up. I just thought of it just now because I was
really
actually
cool.
watching videos on it. But and of course, I don't know how many people would actually have the video of it, because, you know, when your lightning's about to strike, I doubt you're going to be screwing with your video camera.
Just think of an updraft. A lot of thunderstorms, the updraft will be created to where, you know, I've heard of hang glider pilots getting caught in them and dying because the updraft is so strong. It's just a gust of wind blowing straight up from the ground, straight up. It's all that positive potential reaching out up towards that negative cloud. And they were known to go like 30,000 feet up into the air.
So again, kind of into a causal effect, like this thing that you're detailing is causing something else to happen now. So do you want to go into that? Like, where does the downward bias come from, I guess? Like,
well, yeah, let me show you real quick. I have this voltmeter here. It's actually not a voltmeter. It's a field meter. It does a field meter. Yeah, it does electromagnetic field. The I forget what this one is. And
there's field, there's voltage, and there's electromagnetic RF.
Oh yeah, RF. This one's the RF right over here, and this one's electric field. So right now you see it's bouncing around. It might jump up to 30 down here, but it's about 5 volts per meter, right? That's what it's reading. Now I just lift it up a little bit. I'm standing up. We'll see it starts. It still dips down. I think that has to do with the Schumann resonance, but you'll see more of them up higher.
28, 30, 37.
And now when I lift it up over my head,
70. So there it is.
It gets even
right
taller.
Out of the air.
That's the electric field we're talking about.
How does it get affected by being outside? Is there anything inside that they could be picking up? Does it work differently outside with no kind of walls and stuff around you?
It will work differently, and it will also work the same. In other words, what I'm saying is, inside, are there RF signals? Absolutely, there are. We've got the Wi-Fi going. We got, oscillators going from all kinds of different electronic equipment, from televisions. All of these things are generating RF fields, and will affect that. But in this particular mode, where he's looking at static voltage only, that's going to be, it'll probably be more pronounced outside, would be my guess, than inside, because you've just got a change of conditions out there. So, and I haven't actually done this. This is really interesting to watch you do this.
Here's what happens when you put it over. I have a pot of boiling water here.
Okay. Yep.
Wow.
Whoa. Did I steam it out or something?
Looks like an expensive device.
Not really. It was only, I think it was only $105, and I bought it
cool.
Because of all the 5G stuff going on, and I wanted to measure RF pollution in the house and power pollution and, spurious electromagnetic fields and stuff. So that
measures the Sorry, what does it measure again?
It measures power frequencies and like power frequencies like 120 volts, 240 volts, like your normal power fields, like you have in your outlets. I don't know if you use 220 or 110 in Australia.
Yeah, that one's a 220 right there.
Yeah, so you put it near electronics.
Yeah, that's running through the electric field off of that wire right there. If you get it real close to the wire, it'll...
Yeah, the induction from it.
Yeah, and of course, our appliances here run on 220. So, so that makes perfect sense. So anyway, it picks that up. It picks up RF fields. In other words, if you have a transmitter, a CB, a walkie-talkie, a ham radio, it'll pick that up. If you have a wireless microwave, it'll pick that up. And it goes all the way up to 10 gigahertz. So it's got a really robust range on it. And for $105, it's a handy dandy little tool to have.
Absolutely. That's pretty cool. All right. So just off on a bit of a tangent here. I've got Michael Kahn in the chat. He says he's heard that cables carried by the pylons, like the ones out on the streets, like the overhead power lines, are collecting electricity rather than carrying it. My opinion on that, I actually work on these. That's my job. Well, it used to be my job, former job. I used to work on these power lines, going to underground electricity and that sort of thing. What's your opinion on the overhead power lines? Are they carrying electricity or are they collecting electricity?
Well, they're definitely... Oh, go ahead, Zach.
I was real quick. I was just going to say the only ones I could see actually collecting electricity would be the ones that aren't rubber insulated. The ones you see running down your street and stuff like that. There's no way they wouldn't put a rubber insulator on something they were trying to gather electricity through.
Yeah. Those are more guy wires, aren't they? That run down the street.
Yeah, the big tall ones, though, I don't know. That could be. I mean, they're tall. They're real tall, and that's a lot of that's how those guys did it in that video we were watching just now. They just had two towers with a wire connected in between it, and that's how they were gathering that electricity right there. Yeah. So I mean, it could be. I don't know.
Yeah, so my take on that is obviously they are supposedly for the transmission of power. And on the high tension lines, they're extremely high voltage. And the reason they run them at such high voltage is because there's a lot less loss going through those conductors at high voltage than if you stepped it down to 220 or 110, right? Pretty soon you're going to bleed that off to, almost nothing. So they step it way up, into the kilovolt range. And it's primarily for transmitting power. Now, that's not to say that they could not be harvesting an energy at a different frequency off of there. I suppose that could be possible, but I can't specifically name anything that would be doing that. But I'll leave it as a possibility. Let's say that.
For me, I work on these things. So I used to be a transmission linesman, underground linesman, and some of our protections when we were working on the cables, because I was a cable jointer, underground electricity, so they were coming from the overhead power lines, and they were definitely uninsulated. They were bare copper mains, just running between states like that. The big, long, as you said, Bob, they had to step it up into, I think, 132,000 volts here in Australia and up to 500,000 volts. And as you step it up, the voltage, the amps drops down. But I worked personally on the cables and protections from these things. So there used to be operators that switch out the electricity, that isolate what we're working on. And so it kind of goes to earth. In some spots, there has to be multiple earths, just so for one, we know that the power is off, because we wouldn't be able to get anywhere near it if it was on. We'd get blown to bits. But another thing is the protection on the actual cables and the electronics is far superior to anything that can kind of trip it out. So I think they've got a trip out value of something like half a cycle, which is, so we run here in 50 hertz, so 50 cycles per minute, I think it is, or second.
Yes,
per second, so 50 cycles per second. And so they've got a protection value of half of that, so a hundredth of a cycle it would trip out. So if there was anything going through those power lines, you would see when it's isolated, when it's to earth, you would absolutely see something getting picked up from that. So that's something that I have never experienced. And if they were a power collection, just to answer Michael Kahn's question, I don't think the overhead power lines can be a collector for this sort of electricity.
Let me stop you there for a second, Mitchell, because consider this. Okay, the reason I'm leaving it as a possibility, and remember I said it depends on the frequency, and granted, yes, if you get multiple phase frequencies going down there and they start interfering with each other, there's going to be phase cancellations. That's going to cause problem on the power line, right? But what we know about the static field in the ionosphere is that it's DC. Okay.
Direct current. Yep.
So there is nothing that says we cannot have DC and AC running on the same line. In fact, it's done in quite a few applications. So that's why I'm saying I don't know of anywhere that it is being done, but I guarantee you it can be done. Now, the problem is that unless there is some sort of shunt as it gets up to the step-up transformers, as it goes down the line, then the DC is going to get cut off right there, right? Because the DC will not make the transition across the transformer, right? That requires AC to do that. But who knows what's inside of those things? They don't tell us, So that's what I'm saying. It's a possibility. And Zach, also, what is that? What is mine? The GVI? What is the brand of that? Somebody was asking in the chat.
Yeah, let me go check real quick.
Yeah, it's a GV. We're getting it for you. I think it was.
I think it's a 140. Yeah, let's see here. Got it right here. GQ EMF 390 from GQ Electronics.
Okay, so yeah, you can buy it from Amazon. And there it is right there.
That'd be really cool to play around with.
Yeah, that is really cool. So let me hang on a second. I'm going in here. Well, I'm just going to give you the website here, and I'll put it in the chat for everybody. Copy.
Yeah, that'd be cool. So going back into AC and DC, so AC power, alternating current, is something that's how our electricity gets generated, as far as I know, and that's how it gets transmitted. It's got the least power loss. It's got the most applications. So you're saying that the static electricity that is kind of all around us, that's in DC, right?
It is.
Okay,
it is. So now, but the thing about that is here's the thing. Even when it's a DC, of course, all you have to do to transform DC to AC is, run it through an oscillator type of circuit and then amplify that, 60 hertz or whatever you want to do, with the power that's coming in, that 12 kilovolts or whatever that's coming in on the DC circuit, right? So it's easy to convert AC to DC and DC to AC. I mean, you rectify it to go one way and you oscillate it, to go another, right? So yeah, so it's really not a big deal to make the conversion.
So when we're talking, like there's inverters there, little inverters, big inverters, they actually absolutely can convert. But when we're talking about DC, is there current in DC or is it just voltage?
No, there's current in DC and AC. There's current, voltage, watts, resistance. Everything is the same. The only difference between DC and AC is of course, AC is periodically changing polarity, 50 to 60 times per second, typically, depending on the application, and DC is at, positive, negative static.
So in our world around us, do you think there is a current, or it's just voltage that we can measure?
Oh, there's definitely a current. There's a current. You can witness that when you see a lightning strike a tree and it splits it in two. It is the current that is the lethal part, and there's the current also that will kill you. Static electricity doesn't do that much to you. That's why Zach can mess around with his Van de Graaff generator, right? And
I've taken 250,000 volt shock. That's the biggest I've gone. I don't want to go any higher. That one. I saw white for a second. I was like, okay, we're not stepping that up anymore.
Yeah.
But if he had as much as 10 milliamps worth of current at that 250, it would have flash cubed him.
Yeah, it fries your heart, it fries your brain, it does everything. Yeah, the current is the thing that kills you. So when you could have a massive voltage, but it's the current that actually kills you. So my understanding of current is it a potential, or is it kind of always there? Is it something that builds up in DC, or is it something that's constant?
It's a constant. In other words, it's a current. Think about water current, right? A water flowing down a river, electricity flowing down a wire or through the air. That's what a current means. So it is a constant. Of course, an AC current means that it changes directions periodically, right? Every 50 or 60 hertz times a second and stuff like that. So, but anyway, I realize we're kind of getting away from that. I'm going to go ahead.
We are. Yeah. I apologize. Yeah.
Yeah, no worries. I'm going to play part one of Dr. Walter Lewin's. Actually, this is Zach's video. So let's play this, and we'll just listen to what mainstream. I mean, this is MIT, Massachusetts Institute of Technology. This is the United States' premier engineering school. So I would say, yeah, you better listen to this guy as to what he's saying. And it's interesting what he says. So let's go. Oh, crap. You know what? I forgot to share it. Let's try that first. Chrome tab. All right. Now we're ready.
Yeah, and he wasn't a flash in the pan either. He was there for 4 decades.
Yeah. Oh, yeah. Walter Lewin was world renowned. I mean, he's one of the most famous professors of all time. So, okay, here we go.
Hello, everybody out there in YouTube land. This is Good Times for All, or Zach Zambala here if you prefer. In this video, we're going to ask a question. Does this MIT professor confirm electric gravity?
Wonder what the hell holds the nucleus together? If there is such a tremendous force on these protons, well, what is holding them together are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
Okay, and there is a part 2 to this. And now, first of all, I want to tell you something. Even on this, what he's saying, and of course he's saying he's putting it out there because he knows, as well as the rest of us know, Mitchell, that nobody can go out there to test this, right? So he's just saying, okay, well, we really can't justify this here, this mass attracting mass or bendy space-time type of gravity, which is nonsense. So we're just going to say, well, this only works in outer space, right? So, and I applaud him for at least putting it that way.
No, he's a brave soul going against the Institute.
Yeah, I think he actually was blackballed. I mean, they ran him out of MIT on some kind of frivolous stuff, kind of. I don't know. But yeah, he was like blackballed. They took his Nobel Prize away, all kinds of stuff. So they usually don't do that to their own that are playing ball the right way,
Exactly.
you know?
Yeah.
Yep. So, okay. So here's part 2. This is only a minute and a half. So let's play the rest of this, and then we'll talk about this.
Hello, everybody out there in YouTube land. This is Good Times for All, or Zach Zambala here if you prefer. In this video, we will be asking again the question, does this MIT professor confirm electric gravity? Part 2.
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. And now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass.
Now, I want to say that the guys in the EU, the Electric Universe, the Thunderbolts Project, the electrical engineers, Dr. Don Scott, PhD, absolutely disagree 1,000,000% with that. They say that it is all high voltage electricity and plasma that is in fact holding these structures together in the lights that we see out there. Now, I agree with that, not necessarily on the scale that they're talking about, but the fact that, to me, I would agree that it is in fact a plasma type of electrical show that we're seeing up there, right? And we have all the ingredients for it to be that way. We have the scaling electrostatic field, and we also have most of the noble gases, which are, far lighter than air type of gases, which tend to hang out in the upper extremes of the atmosphere. So when you get the interaction between high voltage and noble gases, you start seeing all these funky effects like we see out in space, so to speak, the stars, right? Or even if you're looking at space as water, same type of thing. It's a cymatic vibration, star in a jar type of thing, but you still have everything that you need: frequency, vibration, electricity, and the gases for all these other effects that we're seeing out there. It all makes perfect sense to me when you look at it in a plasma paradigm. So, okay, let's go and finish this out.
The Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force. So even...
Yeah, and again, I don't agree with that at all. And where did they get these numbers, right? How do they know that about Mars? How do they know that about the Earth? And what they're saying here is that the gravitational force in that instance is 17 times larger. No freaking way. Again, this is what Dr. Nakamoto, what's his nuts at New York Community College, Michio Kaku, was talking about when he said, yeah, well, our physics is off by 10 to the 120th. That's exactly
the biggest mismatch in science ever.
Exactly. So,
well, yeah, and Walter Lewin even says that the electric forces here on Earth compared to gravity are 10 to the 26 times stronger. So nothing here on Earth is really affected by gravity. It's the electric forces that he's talking about.
Right. And it turns out that it's all electric forces. Okay. So, the next thing that I think we need, let's see, Zach, you think this is a good one? The force of gravity is electric potential, or should we jump to is gravity incoherent magnetism?
So before we get into that,
okay.
you guys, if you just want to sort that out between yourselves, before we get into that, is there forces going on here? Is that what the assertion is? The downward bias is a force? There is something that is...
in every electrical field, whenever you put any matter inside an electrical field, the denser matter will become positively charged or negatively, depending on what the field is, positive or negative. Here we have a positive field. So it gains positive electric potential when it's in the air, which forces it towards the negative potential beneath it until it hits the ground and neutralizes
something like
out.
lightning? Is that what we would see?
Well, anything. If you pick up an object, you pick up a pencil and you release it, it's immediately going to start gathering the positive electrostatic charge in the atmosphere around it. Therefore, it's going to force down then.
Are you saying if we didn't have that electrostatic charge in the air around us, things wouldn't fall down?
Yes.
That's absolutely what we're saying, because what we're saying is that that downward field that everybody has defined as gravity before has nothing to do with mass attracting mass, but there is a force being exerted electrically on all nuclear material. In other words, there is nothing in this world that is not affected by electrostatic charge. Nothing. I mean, it doesn't matter if it's plastic, wood, gas. And that's another thing that, people definitely want to get into gas. Yep. Yeah, gas is absolutely affected by electromagnetic field or electrostatic fields. We've proven that a million different ways. So there really is nothing that isn't affected. And basically, if you remember, Mitchell, my little experiment that made it in Behind the Curve movie, right? Where I was talking about that we measured the 15 degree per hour, right?
I think, so everyone remembers that, yep.
Yeah. So, but not everybody knows what happened.
Thanks, Bob, apparently. I love to bring that up, by the way, because that absolutely destroys the Coriolis effect, but go on.
Yeah. So anyway, what was going on there, and we had a chance to actually test it and find out what was rotating, right? So just like 100 years ago they had Aries failure, that they proved that it was the stars and the sky that was moving. Today I guess we can call it the Knodel maneuver or whatever you want to call it. But what we did here is we took measurements at a place called Pikes Peak, Colorado, which is at an elevation of 14,125 feet. Okay, then we went directly east of that point on precisely the same latitude line out to the plains of eastern Colorado and dropped roughly about 10,000 feet in elevation. And what happened is the rotation rate increased within that 10,000 foot differential by more than 1.2 degrees per hour. Okay, so what does that mean? That means that as we get closer to the ground, this downward spiraling force that we're calling the luminiferous ether is actually acting just like a tornado, a vortex, right? It's spinning faster, and when it comes down to the ground, you see what I'm saying? If you look at a vortex, the top of it spins slower, the bottom spins faster. Now, why does that debunk the globe? Well, because if we were truly on a globe, we would, if we went and made that measurement at a Pikes Peak and then went directly east to that lower elevation, it wouldn't matter on the globe, because you would still be turning at that 15 degrees per hour, commensurate with the sign of the latitude, right?
That's a good point. So if you're seeing a difference in the rotational, like if there's a difference in rotation from just moving location east, we lost Zach. Is Zach all right? Did he drop out?
Yeah, he'll be back, I'm sure.
Cool. So yeah, that if you so you definitely saw a rotational difference just from changing location east.
We did, and we recorded, and I released it to everybody. The ballers were not happy about it, but after they saw it, it was amazing how little of a squawk they made about it, other than just he's lying about it. It's like
they don't say thanks, Bob, about that, do they? They don't say
no, they don't. Thanks for that.
Thanks for proving there's different rotations just by going east. That would only be possible on a globe, north or south, if you were moving. But that's only in their presupposition that there is a rotating Earth beneath us, and you are picking up the rotation of the Earth in that apparatus. And just by showing that, you go east, that apparatus shouldn't have changed rotational
Not at all. And of course, it's obvious, right? It's obvious that one of two things is happening. And they knew this 100 years ago during the Michelson-Gale experiment, right? Michelson-Gale set out to measure the rotation rate of the ether, right? And they found out that sure enough, it was about 15 degrees per hour. Well, you would have thought then that the Globers would have said, all right, we got Michelson, we got Gale. These are two world-renowned physicists. They measured a 15 degree per hour rotation rate. There is our proof of a rotating globe. Why don't they go to that? Well, the reason they don't go to that is because of the implications when you come forward to Michelson-Morley, and they cannot apply that same logical thinking to a linear type of measurement. It worked in the curvilinear, right? Going around in circle, they're picking up something going around in circle, but they were not getting a linear forward motion of 30 kilometers per second around the sun. And they didn't want to address that. That's why the first thing they came up with was the Lorentz compression, right? Lorentz contraction, excuse me. The Lorentz contraction, which supposedly stated that the device that they were measuring that was in the direction of the Earth turn was actually shortening just enough that it was nullifying their measurements, right? And taking away that 30 kilometer. And then, of course, they were laughed out of science for that. And then, of course, that's when Einstein stepped forward with theory of general relativity and said, dun, 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 let's just get rid
the whole
of the ether.
space-time, contracting and expanding of time concept. Yeah, that's where it all went downhill from there after that observation. So what is it that you think that, this is probably going off a tangent too, but what is it that you think that the fiber optical gyro is measuring? Did you say the ether?
It is the motion of the ether. There's no doubt in my mind that's what it is. Because here's why. All right. For anything to have any of the characteristics, like when we say something is waving, right? Or something travels in waves, like, if you dropped a stone in a pond, right? Well, first of all, a wave is not what something is, it's what something does, okay? So when you drop a rock in a pond, that water, which acts as the medium, starts waving, right? Going up and down. It just starts producing an oscillation, okay? When you play your stereo, okay, and you look at your speakers, and when you play music on your speakers, the speakers are vibrating the sound, right? Which then propagates across a medium, which in this case is the air, okay? And then you hear it with your ears, right? So what I'm saying is, for any type of wave action to take place, there has to be something to wave. There must be a medium, right? Now, light is the same exact thing, right? Now, light is an electromagnetic phenomenon, not an electrostatic. It's electromagnetic. And we know for a fact that we can shine a light through a vacuum chamber and it doesn't even phase it. In fact, it actually allows it to propagate better if you really wanted to look at it that way. But so then you have to ask yourself, so what is the medium for the light to propagate is? And what that is the luminiferous ether. And what's happening is that you are stimulating the luminiferous ether in such a way that the particular bandwidth of the light frequencies that your eyes are able to see, the 450 to whatever it is nanometers, right, actually allows your eyes and your brain to detect those oscillations, right? That's what you're actually seeing. So it's not that light is actually physically traveling, but so much as the space in between you and that light source is being inducted with energy that is vibrating or oscillating at those specific wavelengths, right? So, and this explains why, Mitchell, that, people will say, and I asked this question a million times, it's like, really? So if light is really a particle, then how in the world could you possibly say, okay, I'm going to flip on a flashlight or a laser light and I'm going to shine it through the air. I'm going to aim it at a fish tank. And as soon as it leaves the flashlight, it's traveling at 186,282 miles per second, right? The speed of light, or C. But as soon as it hits the water, it then goes to about 0.6 C, or about 0.6 of that speed, right? Then once it comes out the other side of that fish tank, then it resumes back up at a normal speed of C. Well, how is that possible if light is a particle that it can slow down and then speed back up? Where does that energy come from? That's a violation of laws of physics. But if we are simply inducing an energy or an oscillation into this medium, then it's not a problem for it to change mediums and change the acceleration speeds. So that's something that, you know, and Ken Wheeler talks about this all the time, and he's absolutely right, because we know for a fact that it does behave this way. So I've never believed for 1 second that light is a particle. You know, it is a wave, and it is a waving of the medium, and that medium is the luminiferous ether.
My understanding of how light works is it's a wave function, not an actual wave, not a particle. It is only a probability distribution. The double slit experiment was a great proof of kind of how much we don't know about light. And I'm under the influence that we don't need a medium for light to travel through. So you're saying ether would be the medium. Is there any way that we can isolate the ether or verify that it would be the ether? If ether wasn't in existence, you would say that light couldn't propagate?
That's exactly what I'm saying. That's what I'm saying. If the ether didn't exist, and of course that was one of the things. Remember, when we saw that, the first thing we tried to do was to cut ourselves off from that ether, which of course was silly, because you can't do that. In other words, that's like a fish trying to, you know, cut water out of the fish tank. You can't do it. So we tried encasing the thing in bismuth, right? Because bismuth is highly diamagnetic, right? Well, that didn't do any good. We tried to affect it with a oh crap, what's the magnetic thing? Oh crap, I'm having a brain cramp.
Faraday cage?
No, it wasn't a Faraday cage. It was Lorentz, not a Lorentz coil. It'll come to me in a minute. Either our camera will bring it up. But so we tried to affect it with this magnetic field, and we were able to affect it, you know, but, Helmholtz coil. That's what it was, is a Helmholtz coil. So we were able to affect it with Helmholtz coil. So we tried all these things because, you know, at the time, I had not come across the information yet about the Michelson-Gale experiment, which detected this exact very same ether rotation, right? But back then, they said, okay, so we now know that one of two things is rotating, because we can look up, we see the stars rotating and the celestial bodies rotating at 15 degrees per hour. This can be caused by one of two things. Either they're moving or we are, right? So they had Airy's failure, which was, of course, the optical experiment, and I'm sure you're probably familiar with it. But it was an optical experiment where they filled the telescope up with a little bit of water to slow down the light traveling, right? And they found that if they had to change the angle of the telescope even a little bit more, that would mean that it was the Earth traveling forward. But if they didn't have to fill the telescope anymore, that meant that the light was already coming in properly at that 15 degrees, right? And that they could see it, right? So it didn't matter whether you had the water in or water out, it would still come in and it'd still be visible. And of course, that is exactly what happened. So there we have that proof that there is not only an ether, but that it is moving at a 15 degree per hour rotation. Then, of course, like I said, fast forward to 2019 to what FE Core did. And I'm not even going to take credit for that. I mean, Zach and I and Chris Van Maitre went out and actually did the footwork on it. But, you know, we came up with our solution saying, well, if it's a ball, then it's going to act differently at different elevations, right? Or no, it's not going to act differently at different elevations if it's a ball. But if it is not a ball, it is going to act differently, and it most certainly did. Again, so you've got two different paradigms. You have the paradigm of the vortexual ether, which of course starts in the sky. We're looking at it happening in the sky, rotating above us, that is being contained and being brought to us by the luminiferous ether, and is actually coming down and rotating faster at the ground. Or we have a ball that's spinning, and it just wasn't the latter.
And they also they renamed the ether back in the 80s. A scientist, rediscovered it, and they named it the Higgs field.
Yeah.
So they can never really step away from this. They just gave it another name. So nowadays it's called the Higgs field. The Higgs boson particles and this and that, blah, 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 all this stuff. But yeah, so they just took the ether, scratched it out for 75 years, 100 years or whatever. I think it was in the 80s. So yeah, about 70 years. And then came back and renamed it.
And it was also in the 80s that the United States Air Force redid the Michelson-Morley experiment and found that, yes, there was a luminiferous ether. I have that Greg Braden video, and it's actually published in the Journal of Nature, which I actually have all that stuff. I don't have it brought up right now, but the experiment is published in the Journal of Nature, goes into all the details about it. And every Nobel laureate today will tell you, Mitchell, that, if you ask them, is the ether, is it real? Does it exist? They'll tell you absolutely it does. It must. There's no way around it. And we are the same belief system. And like I said, we've got tangible evidence. Now, it may not be absolute scientific proof, but it's pretty damn good tangible evidence. You know what I mean? So, and that's
it's awesome. You guys like FE Core, you guys doing these things. Props to you guys. Hats off. It is awesome. There's no one else kind of on the other side of the globe argument that is doing this. Is awesome stuff you guys are doing. I apologize for being so critical on these things. I'm just trying to play devil's advocate and
oh yeah, no. Yeah.
The only thing I could.
Oh, sorry, Mitchell. I have one more video I'd really like you to see, because I would like you. I think it would really. It's a physical demonstration that I did, and I think you can actually see what happens when you reverse the electric field in between two plates and reverse the polarity that we see here on Earth. You can actually get things to go and float up and stick to the top plate.
That's awesome. That's something I definitely want to see. But before we move off the topic of ether, the only thing that I could be critical of is probably the speed of light. And I just want to go into that for a second. Has the speed of light actually been measured? As far as I know, it's a two-way kind of a distance has to be there and back. There's no one-way speed of light that can be measured.
Yeah, they say that it has, Mitchell, but I have to say that the details around it are sketchy, to say the least. I mean, one thing that we do know is that we can cause that speed to change by putting it through different mediums. Like I said, you can put laser light through, like if you pulse the laser, right, and you put it through a bunch of water, and then do the same thing in air above it, or even in a vacuum, you will find that the laser propagates faster in the non-liquid medium, or in the vacuum medium, or even an atmosphere, right? So whenever the viscosity of the medium changes, it seems to change that C value. But as far as does it really mean that it stays at 186,282 miles per second? I doubt it. In fact, I think that there are a lot of variables that contribute to that rate of induction. And remember, we're saying that the speed of light is really a rate of induction into the ether. And that seems to be absolutely variable.
Okay, so...
And it's neat because, I was just going to say real quick, light, just like, electricity, falls off at 1 over r squared a lot of times. Yes. If you have a point source, it dissipates at 1 over r squared, just like if you have a point source of light, it also falls off at 1 over r squared.
Yep.
When we're using these sorts of method, sorry, go on, Bob.
I was just going to say, which of course is nothing more than the inverse square law.
Right.
Right. Okay.
And so when we're doing these sorts of observations of tests, do you think you can be sure that it is the ether rotating? It's not just the stars rotating, whatever the stars may be. Do you think you've sufficiently isolated that it would be the ether rotating, not just whatever the stars are?
To my satisfaction, yes. But like I said, since we cannot critically put this through the scientific method, and I fully admit that this is not something that we can manipulate manipulate a variable on, right?
Yeah, you can't step outside of it.
Right. The best that we were able to do was manipulate where we thought it would change its velocity, and it did, right? So what we did is we manipulated the sample of where we took it within terms of altitude. And yeah, that definitely made a difference, but that doesn't necessarily fit into the scientific method, right?
Yeah. So there's definitely a correlation. I don't think anyone can deny that there's a correlation with people.
Yeah.
But like you said, it might not be a causation, but it's a step in the right direction to figuring out where the hell we live and what is going on. So you guys are doing good stuff. Don't like, obviously you're gonna keep going with these endeavors, and it's through going against the grain, sometimes revisiting old knowledge that has previously been visited and strucken out of possibility. These are the things that you guys need to keep doing, and doing great work.
Absolutely. And yeah,
where did you want to go next?
Thanks,
did you want to do?
Okay, I had this,
especially you, Zach, like your demonstrations. These are really cool.
Well, yeah, I've gotten a lot of help. I got to admit, Bob, Cammy, gee, I can't start naming people. Nora Roberts. There's all kinds of people out there that have,
we have friend
really
that's a
helped.
PhD professor, electrical engineering in Greece, that helps us a lot.
Yeah, there's so many people that their minds are going into a lot of these tests, and then they gave me the ideas to try a lot of this stuff. So I definitely can't take credit. I'm just the tinkerer, It's definitely a lot of brains that made this child, I guess, if you'd say it that way.
So go ahead and give us an intro to this video, Zach, what we're going to see, moving different types of matter with an electrical field, and then we'll play it.
Yeah, this is just, I have a Van de Graaff generator, and I take 2 pizza plates, stainless steel pizza plates. And instead of having the positive above and the negative below like we see here on Earth with our electric field, I reverse it. And I put different types. I think it's wood. I put some iron filings in there, and I put some human hair. And I think even a little piece of plastic at the very beginning it shows you. But it'll show you that there is definitely a change in this vector that we're saying is created here on Earth. The vector goes from, pointing down towards, now it's kind of pointing up.
Yep. Okay. So let's go ahead and play this. And after this, Mitchell, we also, we want to show you that, a lot of the other claims, like I said, and we're going to explain to you why relative density disequilibrium does not explain up and down. Okay. And I know you want to get to that part.
Yeah.
So let's go ahead and play this. Here we go.
Oh, I'm not hearing it, Bobo.
Really?
Yep.
Oh, well, my bad. Then let me stop it and reshare it.
Were you hearing it, Mitchell? Oh, you're muted.
I'm not hearing Mitchell. Oh, Mitchell, you're muted. That's why.
I was muted. Yeah. No, I wasn't hearing it. No, I think you have to click on the share audio as well.
Yeah, I did. I thought I did, but maybe not. Okay, so share audio this time and share. All right, let's try it again. Let me know if it doesn't play.
Everybody out there in YouTube land, this is Good Times for All, or Zach Zambala here if you prefer. In this video, we'll be moving different types of matter with an electric field. In a previous video, I showed how I could move a piece of tissue paper using a Van de Graaff generator to charge 2 pizza trays to line up opposite the electric field of Earth. This simply means I put the negative charge on top and the positive on the bottom. As you can see, the paper lifted up from the bottom plate and stuck to the top plate, defying gravity. I had many people ask if other materials could be moved within the field, and I figured out how to do just that. I calculated that with the Earth's size we are given scaled down to 1 foot across, the highest mountain ranges would be shorter than the width of a human hair from the surface. This told me I would have to use very small objects, which to scale would still be taller than the highest mountains. I first started with sawdust. which is just very fine wood shavings left over when cutting wood. As you can see, when I charge the plates, many pieces of wood rise up from the bottom plate and stick to the top and remain there as long as I apply the current. Next, I use iron filings, which I knew because of their density and size might give me trouble. To my surprise, I was able to get the very fine pieces to act just like the tissue paper, while others barely moved, if they moved at all. A very interesting thing I noticed was that some filings raised up into the air, never quite touching the top plate, then falling off in a parabolic arc from where it started. Nonetheless, a noticeable force was applied to the iron filings from the electric field change. Last of all, I used human hair to be my once living organism, as I will not test on living creatures. To no surprise, after the first two observations, the hair also rose from the surface of the bottom plate and stuck to the top, just like the others. I am attempting to create a small, unbroken sphere of water onto the plates, but have had difficulties. Any ideas on making small standing water spheres would be greatly appreciated, so if you have any, please drop them in the comment section below.
Not too many of those.
Thanks for all here.
Nope.
That is really cool, Zach. Yeah, you're gonna have trouble with that spherical ball of water.
Yeah.
That's really cool. So taking nothing away from that demonstration, that's awesome. That's definitely demonstrating that we can manipulate something to cause that change. That's really cool and cause that movement. Would you say that's a force then?
Oh, absolutely.
Yeah, absolutely.
Yes.
That's electrostatic acceleration right there. That is that's just what I was showing right there.
And one thing you have to remember, Mitchell, that it is an axiomatic law of physics that states when you have an acceleration to anything, it has to be caused by a force, right? It's a law. You can't, if you push your car down the road, you're applying a force to the back of it by pushing it. The electricity is applying a force that is causing those things to jump up to the top plate. Anything like that, like I said, is an axiomatic law of physics that when there is an acceleration, going from zero to whatever, that a force must be the thing that's causing it. Now, obviously the question here is what's driving that force, right? And that's where we come back around full circle to this bias or this downward electrostatic vector, right? Now, a lot of people will try and say that, well, in fact, we both know who we're talking about here. Anthony Riley will, try and convince you that his egg in a solution experiment, answers that question. But it's patently absurd because first of all, he hasn't eliminated all the variables for one. And there were several things that could have been done to change the buoyancy, right? I mean, what happens if he would have just let that egg go bad, right? What happens when you let an egg go bad? Do you know how to tell if an egg's bad? You put it in water, and if it
would rise
floats,
when it would float, yeah.
Yeah, and it generates a gas inside of it, right? So does that make his test conclusive? Not in a million years. And then Zach, also, what was the other thing that you were saying to Mitchell before the show?
We can explain away how that actually works. And I even did a demonstration with some balloons in a pin. And I changed the electric potential of it, which is really just density and electric potential go hand in hand. The denser an object is, the more electric potential it can store. So by changing the density of his medium, he was storing more electric potential and it was getting closer to the potential of the egg. Therefore, the egg started rising. Did I explain that properly?
So when, and like you were saying, Bob, when the egg would go bad, the density would change too. So they would actually get less dense. Would you agree? So that's why it's rising.
Well, I don't know if it would necessarily get less dense so much as it's generating a gas inside of it that is converting a more dense matter to something less dense, which is increasing the buoyancy. I'm not a chemical person. I don't know exactly how that works, but I do know how to check for a bad egg, and I know that happens. So
yeah, we know what happens. Yeah, that's something that we can see. Yeah, you put it in water and it floats up, and you know it's no good. But
exactly.
to me, that's kind of changing the density of it, of the egg, and that kind of, for me, that kind of goes in line with the relative density disequilibrium argument. So that like you said, that's the other side of this argument. So you guys are detailing the electrostatic downward vector, and
Right.
yeah, Anthony Riley is kind of detailing the relative density disequilibrium argument. So, but you guys aren't you guys aren't going against what the RDD, the relative density disequilibrium. It is a thing. You're not going against that.
It absolutely is. We're not going against that. What we are saying, point blank, Mitchell, is that it is not what causes things to go down. It's as simple as that, and we can prove that, and we're going to prove that. Okay. Here's the thing with Tony, you know, and all this. I mean, first of all, you know, he complains, he bitches, and he moans that, you know, I haven't worked with him and I'm ignoring him. And well, you know, honestly, there's a lot of bad blood between us because of, you know, things he said to my wife and stuff like that. But I don't like the guy. I don't want to deal with him. He's the kind of person that, you know, he's made several videos calling me a shill because I believe differently than he does, you know, and it's like, okay, whatever, dude. So I just kind of ignore him. And, you know, I'm not about to debate this with him. But so what I do is I just come out with the proof. Right now, here's one of the proofs. And Zach, which video was that you just threw in the? That one you wanted me to show?
Yeah, that was the balloon and the Karen B pin.
Oh, okay.
Button.
So let's go ahead and show this, because we've got actually several pieces of evidence that do show that it is electrical that's causing this downward force. And also the one thing that there are several things that we can do to take buoyancy completely out of the equation, Mitchell. We can completely take buoyancy out of the question. And when we do that, it doesn't work anymore. And
the only thing I want to say about buoyancy is that's got gravity in it. Do you need gravity for buoyancy?
Well, what are we talking about as terms of gravity? If it's in terms of a downward electrostatic bias, yes, you do.
So you're kind of substituting gravity for the downward, like the electrostatic downward.
Yes,
bias.
That's exactly what we're saying is. But we're saying instead of being a characteristic of mass attracting mass, it is a change of electrostatic potential. Okay, and like I said, we can completely eliminate the buoyancy argument. We can render it moot by taking the gravitational so-called field away from it, and we can do this in a couple different ways. But first, let me play this video for Zach. Hang on just a second. So share screen. That one.
Yeah, I think you'll like this one too, Mitchell. This one blew my mind when it actually worked. I was like, no way.
Yep. Okay. Make sure you can hear this.
I'll put it on.
Okay. Make sure and let me know if you don't hear it.
Yep. All good.
Okay.
Hello, everybody out there in YouTube land. Good times for all, or Zach Zambala here if you prefer. In this video, we're going to be taking a look at trying to change the weight of an object by changing its charge potential. What I have is some mylar helium balloons that are holding up a Karen B pin connected to a wire that is connected to the Van de Graaff generator. We're about, 2.5, 3 inches off the ground. And watch what happens when I start applying a charge to it. I'm going to take the negative and get it up here real quick. And here we go. I start applying a charge and look at that. All the way down to the ground. Discharge it, and it raises right back up. Gotta love it, folks.
Now, mind you, we did not change anything as far as any buoyancy requirement, measurement, or anything here. This was done purely with what we are saying gravity really is. No buoyancy ever changed here at all. So continue.
Wouldn't if you were saying, if you're substituting gravity with the electrostatic charge, wouldn't you be changing the buoyancy then? if you're kind of substituting those things.
Well,
That's
well,
only
we're changing the weight of the pin by adding more electric potential to it.
That's right, because the buoyancy factor is going to remain the same, because remember, buoyancy is just a displacement, right, of mass. So, but what we're doing is we're influencing that downward force that causes all things to go down in the first place. And when I say all things, I mean all things. I mean everything, including gases. And so I can safely state, and we'll be able to now prove to you, that gases do in fact go down, go boom, boom. Okay.
that is for me, that's kind of the biggest question for this whole argument. Yeah, can we prove that gases
you better
do go down?
Absolutely. We've applied them in technology now. These ionic winds that are created by a electric potential difference to fly planes, to cool things off. They're using it for all kinds of stuff now. So yeah, we have a video we'll show you about that.
Do you think in just our world around us, like just kind of natural world around us, we can observe that? Not in the apparatus?
Well, yeah, lightning. Well, like when everything is pressure mediation.
Came out today. The video that just came out today by Action Lab proves it, point blank.
Do we play that yet? I don't think we played it yet.
No, we have not played it yet. I'm saving that for last, because it actually it wrecks relative density disequilibrium. It wrecks.
Was this the end of this video? Did you want to continue, or are we going somewhere else?
Let's play the last minute of this, and then we'll go.
Adding a charge, actually. It's very simple. It's attracting to the ground, the negative. We're putting a positive charge on it, and it's being attracted to the ground. Discharge.
I had to hit the negative one.
Negative as well, and there you go, right back up.
Yep. So there you go. And so when I said earlier that all things like electromagnetic, electrostatic, all things are attracted, they want to return back to earth ground. That is, in fact, what is giving us our downward force. It's very real. It's very much there. And we can take buoyancy completely out of the equation. And I'm going to do one more video after this one, and then I'll get to that. But I want to kind of give you a background of where the ether plays into all this. So I want to do one other video that Zach did. And if you have any other questions, feel free to ask.
Yeah, these are great demonstrations, Zach. Love this sort of stuff.
Oh, thanks, man. Like I said, yeah, I got a lot of help, a lot of good ideas from a lot of great people out there. So yeah, thank you everybody who helped.
Okay, is gravity? Okay, I think this is the one I want. Is gravity incoherent magnetism? I don't know if it's that one or if it's the incoherent magnetics of the gravity beast. Those are both outstanding videos. Let's go for the is gravity an incoherent magnetism one. All right, so let's go share screen, Chrome tab, audio, and let's play this. Here we go.
Hey out there in YouTube land. This is Good Times for All, or Zach Zambala here if you prefer. In this video, we will be taking a look at the difference between coherent versus incoherent magnetism. We will again start with some quotes from Ken Wheeler.
Everything is electrical. The only thing that actually defines a magnet is field coherency. Before this thing is magnetic attraction. That which we call magnetic attraction, is it something autonomous from gravity? No, it's not. The only thing that defines or differentiates out the two is field coherency. Something separate and autonomous. Well, here's gravity here, and here's electricity here. Here's magnetism. No, all that shit is the same crap. Like ice, water, and steam. They're not different things. Right now, by any definition of the term, and the force required to move this object, 50 pounds. Wow, that's over a piece of metal. It still weighs 4 ounces if you put it over the dirt or, wood. Yeah, do you know why? Because then we only have one object that has field coherence. I'm not able to induce induction Induction, I'm not able to induce field coherency in a piece of wood or the dirt.
As you heard Ken,
but you are able to induce field cohesion into an electrostatic field, and that's why we feel that it's this way. But the magnetism analog, the magnetism demonstration and analog is a beautiful visual demonstration of this. So let's continue.
Wheeler state, everything is electrical. Not only is it all electrical, but he adamantly shouts that magnetism, gravity, and electricity are all the same thing. The part we will focus this video on is the quote where he states the only difference between magnetism and gravity is field coherency. Instead of trying to tell you what he means, I will show you with a few demonstrations. First, we will take a look at two coherent objects and how they interact with each other. Here we have two cylinder magnets with the north poles of the magnets painted red. As you can see, when I try to place the red ends near each other, the other magnet tries to flip around to align with the non-painted end. This is because both objects are coherent, so the attraction and repulsion are both present. It pushes away when the poles are the same and attracts when reversed. Now we will take a look at how multiple magnets, when not aligned, become incoherent. First, we will observe the magnetic field when the magnets are all lined up and coherent. As you can see, the more magnets we align pole to pole, the stronger the magnetic field gets. However, this is the complete opposite when the poles are not aligned. As you can see, the more magnets we add to our incoherent mass, the weaker the magnetic field gets. Now let's take a look at how a coherent object, the cylinder magnet, interacts with the large incoherent mass of magnets and ball bearings. As you can see, the red pole of the magnet is attracted to the mass, so we might assume that the bare pole of the magnet would repel. Yet this is not the case.
No, that right there is huge, right? Because magnets, if that was any normal magnet that was coherent, it would repulse it. But here's the thing, that in an incoherent situation like that, the force is always attractive, right? Just like what gravity is. It's always attractive towards the earth, towards downwards. And the reason for that is because we're using one side of the modality, analog modality of the luminiferous ether on the magnetic side. The other side of this is, of course, the electrostatic side of the coin. But one gives us a beautiful demonstration that we can then apply as far as a conceptual visualization for the other. So let's continue.
As I flip the magnet over, the bare end is also attracted to the mass. So how does this relate to what we are calling gravity? Like gravity, incoherent magnetism is an attractive-only force. No matter which pole of the magnet is placed near it, the incoherent magnetic field is always attracted and never repelled. All matter is made up of charged particles, and like magnets, these particles have poles. The Earth and everything on it is ultimately a huge mass of charged particles. This is why everything is attracted towards the Earth. There are a few apparent exceptions to this rule, like helium, balloons, and rain clouds, and we will cover this in another video.
Okay, so basically, that's pretty much it, how that goes. Now,
isn't that awesome? The slinky.
Oh, I know. This is really cool.
The bottom never moves. It's always the top.
Top coming down.
That forces the bottom to move.
Yep. Slow motion. Yeah. And again, once again, there it is, that downward force. It comes up everywhere, Mitchell. I mean, there's no getting away from the fact that it's there. Now, let me ask you something. You are familiar, I would assume, with what's called a density tower, yes?
I am.
Okay. And what can you tell me about density tower, and how do you believe it works?
So I believe it works in line with relative density disequilibrium. So you've got objects of a density, and when they're in a specific medium, they're going to either go up or down relative to that medium because of their density. So that's where for me, that's where relative density disequilibrium comes from. If it is out of equilibrium, we're going to get a movement. Whether it wants to go up or down, its relative density in the medium will determine that. And that's what we're seeing in a density tower. So we've got different objects of different densities. We've got different mediums of different densities, and they sort themselves out into their various equilibriums.
Okay, fair enough. Cool. So what would you imagine would happen then if we took a density tower up into a 0G vomit comet plane and we shook it up and looked at it while the plane was in its parabolic arc, effectively eliminating our gravity, right? So we're kind of emulating a 0G force. What do you think that density tower is going to do?
Yeah, it goes nuts. But I've seen this happen. Let's look at this happening. You've got a video on.
Yeah.
Yep.
Okay.
It's happening. Yep.
And I'm going to explain why it happens. But yeah, let's go ahead and do this. Let's see.
To show that oil floats on top of the water. This happens because the
I don't think we have to go through all of this.
That is, they
Let me
do not mix. And
pop
B,
it forward. Hang on.
densities much.
Yeah, probably just
Here's a
the
tower with
bit where it's into 0G plane.
Vegetable oil.
Yeah. All right. So.
It's right now.
Okay, let's turn it over to John to see the fluid in action.
Density tower. It's got different liquids, different densities. So right now we're in the microgravity, so these are really separate. You have F272, water, and vegetable oil. And as soon as we hit zero, as soon as you go into microgravity, well, you'll see. 0. Science!
Okay, so as we can see, he shook it up. It does not want to reorient at all. Now, I have heard people complain, well, it didn't have enough time to, but I would ask that you provide a little leeway and understand that they've done this several times. There are other Carthage College videos on this. It never reorients. So that's one thing that I want everybody to see. Now, the interesting thing about this is, and I was not able to find this video before the show started, so I apologize. So I'm just going to narrate what happens in the other video that, when I first did this demonstration a couple years ago. They did this very same experiment again, except this time the pilot went over the arc, kind of exaggerated the arc, which caused everything to kind of float up to the top of the fuselage. In other words, he was overcompensating. So instead of just being floating in the middle of the fuselage inside of it, he pushed over a little bit more, and it caused a slight bias to the top side, right? So then what they did is they shook up the density tower for that. And what did it do? Well, the amazing thing is all of a sudden then it started working again, but this time it organized in the opposite direction. Right? So the fluids went from density, less density to higher density down. But when he put it over the top and changed the emulation of the force of gravity, if you will, to the top side, then all of a sudden it went to the upside. And it's like, okay, but the point here is that unless you actually have some sort of a small bias, some sort of a small force that causes this to happen, then buoyancy is rendered moot because it can no longer separate from the constituent parts of the other liquids and the other viscosities in the density tower. Okay.
Yeah, the dense doesn't know which way to go.
Exactly.
It kind of turns that off, and that's what we're saying. You need to have that little switch turned on just to throw it's a very weak bias. Just like they claim gravity is, it's very weak. Well, this electrostatic force is very weak.
Yes.
And without it, though, you don't get that denser medium, that denser object wanting to go towards ground.
The only thing I can comment on with something like in a zero G plane is just such an unnatural position for anything to be in. It's literally just things kind of falling out of the sky. If you didn't have that plane around the density tower, it'd just be that tube falling out of the sky, and that's such an unnatural position to kind of judge why things happen in that circumstance. But it is a cool demonstration of.
Yeah, well, it's
well, yeah, but when you're judging why things fall, you have to drop stuff, right?
Right, and what we're
when you're
determining
trying to
here
test it
is why is it that these density, why is it that the density tower is working? Why does it require either the downward force of gravity to work on the ground or to emulate that force in the opposite direction to work in the zero-G vomit comet? I mean, again, when you put it in an absolute zero-G, it doesn't work at all. And that's what I'm saying. It renders the relative density disequilibrium moot completely. Right. Now, let me show you one other thing that really kind of throws a wrench in this as well. And you're probably familiar. I've talked about this before, about gravimeters and what they do. Okay. So what a gravimeter is, basically in its simplest form, here's one of these, and it's wow, what is that noise?
Oh, sorry, that was probably me moving my microphone.
Oh, okay. So someone's going. All right. Anyway, so what these are in their simplest form is they don't, contrary to what they say about they measure gravity fields, that's bullshit. There is no gravity field. Okay. That's horse manure. What these things do is they measure rates of acceleration, right? Rates of acceleration changes. And what we found out about these things and the way they do it is they do it with a laser interferometer, much like the Michelson-Morley type device. And essentially, so what happens is this. Inside, they have taken a ball, right? And they put the ball inside of an evacuated tube. So what does that mean to be evacuated? Well, if you evacuate a tube, you have now taken out any matter whatsoever. So there is nothing, we have taken any variable or any possibility of anything working against a different density out of the equation, because there is no other density, right? There's simply a ball that is falling through an evacuated tube, which has absolutely nothing in it, okay? So what happens then is as soon as it's released, as soon as you hit this, it drops the ball through this evacuated chamber, and of course it's being tracked with the laser interferometry, which is, accurate to within 12 parts per million. I mean, or something like that. It's crazy accurate, right? And so what it then does is it renders back a rate of an acceleration, right? So what we know is when they do this, the acceleration changes from place to place on different parts of the Earth. And like I said on the Globebuster show, the other day, on Wednesday, I said that it's interesting, but whenever there are areas of magnetic anomalies, the gravitational field also seems to have gravitational anomalies. When there are electrical anomalies, like lightning strikes and stuff like that, coincidentally, this downward acceleration field also seems to be affected, meaning that there is something that is directly involved with electricity and electromagnetism and the ether, of course, which generates them, which is causing this downward bias that is being put on everything, right? Now, the other thing that makes gravity so-called an anomaly, and nobody can explain this, is that it doesn't just fall. It just doesn't go down. But from what we can tell, it keeps accelerating, and it keeps accelerating, and it keeps accelerating. When we watched Felix Baumgartner jump out of the plane, right, he got over supersonic speeds before he got into enough atmosphere to slow him down, right? So, and again, what did I tell you earlier about an absolute axiomatic law of physics? When something is in a state of acceleration, there must be a force applied. The question is what is that force? That force is the electrostatic downward bias that is being caused by this electrostatic difference of potential and not mass attracting mass. But to deny that it's there is foolhardy, because it absolutely is. Now, to get to the question of Nathan Oakley, where he says, no, gas doesn't go down, it doesn't go boom, boom, he's wrong, point blank. Because if you
before we get into that, can I just address some of the things you just said?
Sure, go ahead.
So for me, when Felix jumped out of that plane, he's going through the medium, and the medium's slowing him down. So for me, it's like relative density disequilibrium is all about the medium and what you can manipulate in the medium. Mm-hmm. And that's what I'm seeing when Felix jumps out of the plane. The medium is slowing him down. What are you saying that speeds him up? You're kind of being in that part of the equation. What speeds him up? So the bit about disequilibrium is everything here on Earth is it wants to find equilibrium. And so when someone takes themselves, like he has in a plane, he takes himself out of that equilibrium. Equilibrium is down the ground here, where that's where he'll rest, down the ground. If you take yourself out of equilibrium, you're going into disequilibrium, and it is trying to find that equilibrium. And I think that's where you're bringing the electrostatic force. So you're trying to say that the cause of things ordering themselves into the equilibrium is due to the electrostatic force. Is that what you're saying?
Well, yeah, the electrostatic gradient, because we have this electrostatic gradient for things to line up in.
That's right. We're always being pushed down by it. Everything is.
Okay, so let's go on to the gas then, because that's okay. The next question.
So let me ask you one other question though, really quick. Would you say that once Felix got down, right, and he landed, popped his parachute, and got down on the ground, and he was on the ground, he was no longer going down, would you say that he had achieved equilibrium?
When he's on the ground, I believe that if he was just laying there on the ground, yeah, he's in a state of equilibrium for his density within that medium.
Okay, and what would you define equilibrium as at that point?
I suppose something, so the object in the medium when it's no longer moving, when it's at rest.
Okay, well, but it's still exerting a force. That downward force is still present because of the fact he's got a weight that is pushing down.
So it kind of, this is the part where it's hard for me to come over to that side of thinking, because that's when the globe believers say gravity is always affecting something. So you got a coffee cup on the table there, it's at rest, but they're saying that gravity is still pulling it down. And that's kind of what you guys are saying. I see things at rest because they're in equilibrium, but then you guys say that there's still a force acting on it, but we don't see that force.
It weighs something, so there is absolutely a force acting on it. Otherwise, it wouldn't have any weight. And weight was one of the original things that was absolutely defined as a force. Of course, we know that if we put our weight behind pushing a car, right, we're applying a force to it. So weight is definitely a force. So just because you have met the law of Newton's action reaction, by the ground pushing up at the same weight that you're pushing down, that doesn't mean that force is gone. It's still very much there. Okay. And that's what we're saying. Now, as far as getting to the idea, and you've heard this before too, when they say, well, no, gas disperses in all directions. It's like, no, it doesn't. It will disperse in all directions. And yeah, energetically, it will be bouncing around all over the place and hitting itself and, all that. And then eventually it's going to slow down, and, that energy is going to kind of dissipate. And the natural downward electrostatic force is going to cause those gas molecules to, again, go towards the down direction. And I'm going to prove this in just a minute, okay? But I want you to think about something, Mitchell. If relative density disequilibrium requires another medium right, to be able to go through, either pass through or float upon, be buoyant upon, right? What happens when you have removed all other types of medium and there's no other medium left? And when I say that, I mean, what happens then if we take a vacuum chamber and we evacuate it to 10 to the negative, whatever we can do, the best we can do on Earth, right? And then we fill it up with some helium gas. Is it going to float up? No, it's not. It's not going to cause it to get lighter or anything like that. But because of the fact that the gas, you know, when you first put that helium gas in there, it's going to go bouncing all over the place. But eventually it's going to come to rest on the bottom because of two things. One, because it's run out of energy, you know, from moving around all over the place. And two, it's going to change states. Also, it's going to change to a liquid, you know, for another thing. And it is, it doesn't have anything to be buoyant upon. All right. There's nothing to be buoyant upon.
So
Sure.
those 2 points there. So what we know about gas law is, by gas bouncing around all over the place, that is not a reason for gas to lose its energy. That is what is called an elastic collision rather than an inelastic collision.
Anamorphic.
And elastic.
Anamorphic,
Sorry?
I think, is what you're looking for.
Anamorphic. But gas bouncing off its container in itself, it doesn't lose energy. It keeps the same energy. So you have a gas, if you had a perfect container, which I don't think that's possible, if you had a perfect container where no gas can escape at all, there'll be no diffusion at all, I think you would, well, gas law states that if it would stay at the same pressure, it would not lose energy, it would stay at the same pressure, just by having
ask you something.
gas.
If I go and I fill up a tank full of helium, right, and I carry it around and I carry it home, right, and then I get home and I shake it a little bit, all of a sudden it's now liquid at the bottom. It's clearly liquid at the bottom, right? So clearly it's changed state, right?
Changes phases, yep.
Yes, it's definitely changed state, but it has come to rest on the bottom. Okay. And even if it's in the gaseous state, now I'm going to play this next video for you. And this is what absolutely puts this away. And like I said, I cannot even believe that this video came out today. I mean, talk about serendipity. Holy cow. So let me stop sharing. Hang on a second. And then I need to reshare with sound. And Chrome tab. All right. So I'm just going to play this whole video. It's 5 minutes, but pay close attention to it because, like I said, this absolutely annihilates relative density disequilibrium, point blank. And then you tell me what you think. I mean, I may be wrong, but we shall see. Let me do this. And all right, here we go. And this is for fair use, by the way. So hopefully this guy won't strike us on it, but he shouldn't, because this is absolutely for fair use for educational purposes and all that other fun stuff. Here we go.
In a vacuum. And I'd like to thank Morning Brew for sponsoring this video. I'll tell you a little bit more about them later on in the video. So I have a plastic bottle with air in it. Right now, if I weigh this on the scale, I'm actually only weighing the plastic bottle because I have air inside the bottle and outside the bottle. But if I remove the air from around it, then I'm weighing a different thing. I'm actually weighing the plastic bottle itself, and I'm weighing the air inside of it. So let me show you what I mean. I'm gonna put this empty bottle on a scale in the vacuum chamber, and you'll see that when I remove the air from around it, it suddenly starts to get heavier. Okay, let's put our empty bottle on here. So right now it weighs 11.434 grams. Let's turn on the vacuum. And it immediately starts gaining weight. It's already gained 0.3 grams. And I should mention that we're using grams here. This is a measure of mass, but when you use it for a scale, you're actually measuring a force, not a mass. And it's called gram force, abbreviated GF. What?
Okay, so mind you what he just said there. You're actually measuring a force, okay, not a mass. So let's keep going.
It's at 12 grams already now. So it's gained almost 0.6 grams, over a half a gram of weight, just by removing the air around it. Now, this effect doesn't just happen for air in a bottle, but it happens for anything, including you. For example, I have this guy here standing on my scale. So he's starting off at 19.81 grams. As soon as I turn on the vacuum, though, he starts to gain weight.
And of course, the reason why that's happening is because there is a slight difference of buoyancy between the little doll here and the air inside, right? But when you evacuate that other buoyant media, he's actually getting heavier. So he's dropping down. He's then succumbing to that downward force that is pushing him down. So let's continue this.
He's already gained around 0.02 grams already, 20 milligrams. 19.84. So he weighed around 0.15% more just by being in the vacuum chamber. Before we continue with our experiment,
let's not. He's going to do his little advertisement. Let's jump up ahead to where he is done with that, and that's at 3:04. Okay, so he's done with his advertisement. Let's continue on with his video.
Now let's get back to our experiment. So you don't notice, but the air all around you actually has some buoyancy to it. So buoyancy is the force up that you feel in a fluid. And that force up is equal to the weight of the amount of fluid that you displace. Now, normally we don't notice the weight of air because we're in the air. For example, if I have this bottle here and put it in water, you'll notice that it floats. That's because there's air in the bottle. But if I put water in the bottle and then put it in water, so it has a little bit of weight, which is the bottle. Now it sinks. So you can see the outside of the water on this hanging scale here. It weighs over 250 grams, so it maxes out the scale. But then when I put it in the water, suddenly it's not heavy anymore. So it weighs essentially nothing on the scale. It does have a little bit of weight to it, and that's the weight of the plastic bottle. If you imagine the air as water, you can see that the plastic bottle had air inside and outside of it, so we can't measure the weight of that air because we're...
All right, and remember that both air and water are considered to be fluids. Just thought I'd throw that in there.
In the air. But as soon as you remove the air from it, then suddenly you can measure the weight of that air. So it makes it as though the bottle weighs more with the air in it. This is the same reason why if I put helium balloons in a vacuum chamber and then reduce the air pressure so there's not as much air around them, eventually the balloons will fall even though they're filled with helium. Because even helium is heavier than a vacuum. That one fell.
Went down, went boom, boom.
Stop floating. Hey everyone, thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to subscribe if you haven't subscribed.
All right.
All right. Let's go through what we're seeing here. So it's not the helium itself going down, go boom, boom. It's the container the helium is in.
Rubber. Absolutely it is. Yes.
If we popped the rubber of the container of the balloon, the helium would expand in all directions as per gas law. I haven't. Is there anything you can show us to say that it wouldn't?
Wouldn't it have turned into a liquid also with that amount of pressure and no more gas particles to really bounce off of? It's not like they're doing that into the gas, into a gas, into a gas. There's a lot of space in between them. But so it isn't that molecular thing that we see here on Earth where we always have atmosphere. In a vacuum chamber, that helium balloon wouldn't fill up the whole space. It wouldn't, you know what I'm saying? It would only fill up,
expand, evenly. But it's when it goes into a liquid state or it's transitioning to a different state of matter. That's when the density of it changes, and that's when gas law doesn't apply anymore. It's now a liquid. I know you can say that they're both fluids, but then it's not describing the state that they're in. This is my train of thought, like way of thinking of what's actually going on here. Unless I can actually see a helium in a gaseous state going down.
Well, yeah, the opposite way is we could say, show me helium going up in nature. Can you do that? You know, we could reverse it. You don't witness helium going up in nature ever.
So my train of thought is
not until you contain it can we witness this.
Well, the very fact that we have gas is the proof that we are contained. So I think we're always contained, but if it is releasing helium into just the air around us, I don't think we have an upwards force. We don't have a downwards force. That's just my opinion on this, as per kind of my understanding of the natural laws. Gas expands evenly in all directions. That's how the gas.
Well, when you get a gas that's heavier than another gas, which direction does that gas go?
So back to relative density disequilibrium.
Yeah,
it appears
but you could also say it has more electric potential, therefore it's forced down to the ground. The only thing that accelerates is when you drop it and it goes down. Nothing accelerates upwards. Nothing. Not a helium balloon. Nothing accelerates. A helium balloon goes up, but it goes up at a relatively constant speed. It doesn't speed up and speed up and speed up like when you drop something from a high altitude.
So the explanations, demonstrations that you give us, is this in any way disproving any gas laws, though? Because that's what it would kind of have to do. Well,
no, because it's all related to electricity, and density is also related to electricity. The denser an object is, the more potential it holds.
Yeah, no, it doesn't. It does not disprove any gas laws or anything like that. In fact, it doesn't. The only thing that we're saying is that this downward force, not only are we saying that it's there, which like I said, dude, it's blatantly obvious that it is. We can measure it. We can't even do ballistic calculations without figuring the G-force, all of this stuff. It is absolutely positively there. We're just saying that the cause of it, the causal effect, is electrical, not bendy space-time, right?
Definitely.
So
yeah.
you have to ask yourself, why, Mitchell, why do things go down? What is it about down that makes down down? Why doesn't it go to the left or the right or anything like that?
So when we're talking about gas expands in all directions. So it's not just going down. It's not just going up.
No. You can't say that, though, because not all gases do. Denser gases go down. They don't expand upwards.
But if given enough time, like you guys said before about the density tower, like given enough time,
nitrogen
with
down
gas,
here where we're breathing, and yet that nitrogen is not up there in the helium regions. It's well below it. So to say that they're mixed all over the place, no, I don't think so. In fact, there is a definitive and distinct layering of gas the higher you go in the atmosphere. Now, obviously, yes, it's contained. There's a firmament there, and I know that, you know that. But the point is that even the gases are, just like in the density tower, are layering.
For my experience of how we view gases just in our air, in the container of whatever our air is, it is a dynamic system, and I can't.
Oh yeah, for the most part. But once you get so high, what is it? The stratosphere. All the winds stop. All that circulation, all that gaseous movement, kind of stops up there. It's like it's calm. That's why they fly a lot of the air balloons at a certain altitude, because everything kind of levels out and evens out.
That's right.
I wouldn't say there's just less of it. So something that we can definitely demonstrate is 75% of all our gas here existing on Earth is between 0, which is ground level, and 10 miles. And then 75% of that gas existing in that 0 to 10 miles is actually just between us here and the clouds. So it's more of an argument of, sorry, I'm just going to clear my throat. It's more of an argument. This is horrible. Sorry.
I hate it when that happens.
I know.
Apologies. So it's more of an argument of it's just getting less of those particles up there when we do go up. I think we still do have nitrogen at high levels. There's just less of it, and there's more.
That's right.
Of the helium.
Because in general they obey that, and they also do layer. And you have to ask yourself, why do we not fill up these balloons with nitrogen instead of hydrogen or helium? Why? Because of the density of the gas itself, right? So we know just by the density of the gas itself, it's going to want to climb and rise above and sit on the very top layer of all the other gases. It's not going to mix in with them. To some degree, yes, it is. But for the most part, you're going to have a layering of gases, and depending on the weight of those gases or the electrical, I just, what is the word I'm looking for? But the electrical condition, electrical specifications of the gas is going to be what causes it to give us our density layer of gases, our density tower of gases. So
do we actually have those layers, those individual kind of separated layers? I thought everything was just like a homogeneous, inhomogeneous.
No, they claim it. Yeah, they claim it once it starts getting up there real high that you have your, the argon and then this one and that one, and hydrogen is the one at the very top. Hey, I'm sorry, Hank, just settle down. But yeah, hydrogen's at the top, and that's what they claim at least. We've never been able to send anything up there to fully test it ourselves.
Yeah.
So just like, a lot of the stuff we have to say as our evidence is coming from them.
That's right.
I mean, I've never tested the air. I've never tried it. So I really, we're taking the words of these people that we don't trust in the first place. I've never tested air density and this and that.
We also have to extrapolate on common sense, right? We have to look and observe what's actually happening here. And like I said, Mitchell, the fact that the density tower in the 0G plane, when you increase that downward vector of the plane, which causes things to float up towards the top of the plane, which causes the density tower to rearrange in that opposite direction, tells you point blank that there has to be a bias there in order for the density tower to even function. Without that bias there, either up or down, the density tower doesn't function at all.
I think if we show him the one with the ionic wind, the video with the ionic wind, he'll understand the gases a little bit more. Remember, electricity is equipotential. The more you make it, the stronger it gets. But even at very small levels, these forces still exist. You point your finger out, there is electrostatic charges coming off your fingertip. You can't see them. They're microscopic, teeny tiny, but we know they're there. It's just how electricity works. It's scalable.
Yeah, which one was it called? I don't remember the name of the video, Zach. Can you grab it?
You showed it to Mitchell earlier, I know.
Oh, is it the force of gravity is electric potential?
That might be it, yeah.
Or
no, I thought it was, does gravity affect, or electrostatics affect gases?
Oh, yeah. Yeah, let me find that. I actually had that pinned in my email.
While you're grabbing that, so where the relative density disequilibrium all comes into it with me is everything is like in the vacuum chamber. When you remove the density of the medium around it, it still falls in line with what relative density disequilibrium
explains. We're not. Oh, sorry. Go ahead.
So I know you guys are definitely aren't disproving or going against what dense objects do in mediums, but to say there's a downward bias, I'm still skeptical. I'm taking on board all the stuff you guys are saying, all the stuff you guys are presenting. I'm probably going to have to go through this video again and rewatch it, but it's still kind of a barrier for me to get through to come over to being definitely a downward bias, because the way that we view gas for me is the biggest hurdle that I would have to get over to
This one should help. This one should help.
Yep.
You just got to remember there's an electric potential difference from the air above to the air below. And because electrostatic forces will move things in that. The denser the object, it will push that one as far down as it can, away from the positive above towards the negative below. Now, just like other things, if it comes on something denser, maybe a denser medium, denser gas, it will stop and become buoyant. But that force is still there. These are the laws of electricity. Any matter within inside of an electric field will have a slight force applied to it. That's one of the laws of electricity. That's all we're saying, is the laws of electricity do apply to this place, and from what we can measure,
and that's why we call it a bias.
They work.
That's why we call it a bias. I mean, it is by all definitive terms of physics, It is absolutely a force because it is providing an acceleration. That is indisputable. That is an axiomatic law of physics. Okay, so it's a force. We're just trying to determine what that force is that's causing this. So let me go ahead and play this real quick. And Zach, if you want me to stop for any commentary, just let me know. Okay.
Will do.
All right, here we go.
Too bland. This is a good time for all. There's Zach Zambala here if you prefer. In today's video, we're going to answer the question, does static electricity affect gas? Now the answer 100% most certainly is yes. We will go to ionic wind is what it is called. Ionic wind in nature. Wind charged molecules in the air are subjected to an electric field. Now, everywhere on Earth, there is an electric field. Please, if you think you know a place, I would love to hear about it where an electric field has not been measured on Earth. So, wind charged molecules in the air are subjected to an electric field. They are accelerated. And when these charged molecules collide with neutral ones, they transfer part of their momentum, leading to air movement, known as ionic wind. We've known about this for quite a while, known about for centuries. MIT, fly first ever plane with no moving parts. This one's pretty interesting right here. This is the popular mechanics. If you type in ionic wind, popular mechanics, this one should pop up. It just talks about how long we've known about it, how it works. MIT was able to create a focused wind that reaches 200 miles per hour. It charges the atmosphere. And when you have the negative back here, it forces all the charged air particles to flow towards the negative real fast to try to neutralize. These are the basic laws of electricity, folks. 1672, corona discharge. 1750, the electric fly. That's pretty neat. He had an S-shaped wire, kind of like a pinwheel. It would cause it to spin, having it facing in two different directions. Visualization. Of the air flame from an electric spark in a vertical jet. I don't know. This is pretty neat. How I control gravitation, 1929. But yeah, really neat read. This guy supposedly 1964, the Ionocraft.
One other thing also that I think you've seen it, Mitchell. Have you ever seen the demonstration done by the University of Bristol where they're talking about spider ballooning?
Yeah, I've seen spider ballooning. Yep, definitely. They're manipulating some sort of electric charge in order to float. It's pretty amazing.
Yes, exactly. And that's exactly, of course, they say, NASA says that that's also how they control some of their high altitude balloons. They also say that they do it with satellites, which we know is BS, for two reasons. One, because there are no satellites, and two, because in space, you wouldn't have enough material to be able to collect a charge onto, right? So that annihilates that. But the point is that the spiders are able to release a little bit of silk and then change the electrostatic potential on that, which allows them then to defy gravity and navigate up and down within it, right? So again, all we're doing is we're just bringing all this evidence that says that this downward bias that we're talking about is absolutely an electrical phenomenon. And the idea that it's bendy space-time is just retarded, right?
Absolutely.
There's
no question about that. Yeah, I think that we get, there's no argument there. Bendy space-time doesn't even come into this conversation. It is all about, whether there is a downward bias and whether it's caused by the some sort of electric effect. And so when the spider manipulates its web to do its ballooning, is that I suppose it has to be aware of the electric charge surrounding it.
It is.
And
in fact,
and
they said, they said basically the way it detects it is there are little hairs on its legs, and they could tell when they energized that field at the University of Bristol, because they did this completely under controlled conditions, that they observed the little hairs, on the spider's legs stand up, just like, you see a cat or a dog, the hairs stand up on the back of their neck, whatever.
Or the hair on your arm when you get really electrostatically charged.
Yeah. So that's how they detect it. And then they know it's there. And then what they'll do is they'll raise their abdomen and they'll shoot out a little bit of silk, and then they'll charge that silk, and off they go, man. Anti-gravity, just like that.
And just like the laws of, electricity dictate, you'll notice when they do it, they always walk to the point or tip. They never do it from the middle of a leaf or something like that. They always want to be near the tip. And there's more electric potential when a surface has a sharp point to it than if it's curved or if it's flat. That's just the way electricity works. They have a bunch of math for it and this and that, but I've tested it. I have the electroscope and stuff like that, and you can actually test these things. That's why I went out and bought all this electrical equipment, because I wasn't going to just take Walter Lewin's word for it. That's why he is such a great teacher. He does so many demonstrations for his class. He doesn't teach anything from the book, but what he teaches you goes along with the book, he says. He explains it very clearly, So I went and did all those tests. I wanted to try them and see if I got the same results. And wherever I did it, Indiana, Colorado, South Carolina, wherever I'm doing these tests, they all come out the same every time. The laws of electricity, in my eyes, are sound.
Yep. And the other thing, of course, that relative density disequilibrium cannot answer is the question of why are there different acceleration rates on different parts of the world? Now, in our model, we can answer that quite easily. But like I said, first of all, you cannot deny that these acceleration rates definitely they definitely change. You have different gravitational fields when you have anomalous magnetic fields. You have different gravitational fields when you have anomalous electrical fields. But the point is why is it changing at all, right? Especially when you have removed any buoyant variable out of the equation altogether. I mean, there's nothing buoyant. There is nothing to be relative density against. We have eliminated that with the vacuum. And yet we still have acceleration changes that are registered quite accurately by the accelerometer. This means that those changes have got to be coming from outside the device, and it is clearly, in our opinion, an electrical field that does that. But just the fact that it does happen annihilates the relative density disequilibrium, because it cannot explain that.
Well, there's a word you keep bringing up, buoyancy, and that's me personally, I don't include buoyancy in the relative density disequilibrium, because buoyancy has, like we said before, the gravity equation built into it. So it's only observational. So it's more the relative density. Isn't buoyancy just the other side of the disequilibrium? You have density, you have buoyancy, and so
something has to go up when something goes down.
That's right.
So I think that's where the confusion of what we consider relative density disequilibrium actually is. It's not buoyancy, because buoyancy would say that there's an upward force being applied. It is all due to just the medium.
Buoyancy doesn't imply that in our model at all. Buoyancy is being displaced. There is no upward acceleration. Like I said, nothing accelerates upward. No helium balloon, there's nothing that it will accelerate upward without a very strong force. And eventually it'd come back down. Right. The only direction things accelerate towards is down.
And that is just a fact. Now, it's the way things are. You drop things, I hate to be coy about it, but when Neil deGrasse Tyson simply dropped it, Yeah, I agree. You can say, well, yeah, that's because it's gone through a higher density to a lower density or whatever. It's changed density medium. That's why it does that. No, that's not the only reason why it's doing that, because something is causing that from going to 0 miles an hour to, you know, depending on how long you can let it drop, it keeps accelerating. And as we said, an axiomatic law of physics states that when you have an acceleration, there must be a force. Well, relative density is not a force, but electrostatics is most certainly a force.
An example I'd like to bring up is where gases get produced in the first place. Like I'm definitely taking on board everything that you guys are putting out.
Oh yeah, well,
we're going to get you, Mitchell. We're going to get you.
Yeah.
I'm being hypercritical. I want to cover all my bases here before I can kind of make a really good informed decision. So
I got a good video you could watch that we won't show you here because I think it's 16 minutes long. But the video where I kind of put all this together. Yeah, that's a long video for me now. 16 minutes. This one took me like a month to do. But yeah, I mean, I'll even show you. I can bend still water. I can make still water have a curve in it. Using electrostatic forces.
Okay. Yeah, that'd be cool. That'd be a good demonstration. So, but the example I want to bring up is as far as we know, all gases, natural gases, are produced here at ground level, and they're not just sitting on the ground. They're going up. Would you say that's an acceleration, like when they expand up into the air around them when they're not sitting on the ground?
It's an acceleration, but it's caused by a buoyant force. So yes, because
but it doesn't accelerate. I wouldn't call it an acceleration because an acceleration, but then it kind of steadies out almost instantly and starts rising at the same pace.
It's a limited acceleration because it goes from 0 to whatever, right? And then but the difference is the downward acceleration. It keeps going, man. Especially if you remove any medium, it just goes faster and faster and faster. And as far as we know, we don't even know what the limitation of it is. We've seen things go supersonic. We know that if you shoot a bullet into the air and it goes up, a mile or two and then comes back down, you better get the hell out of the way because it'll kill you, right? It's going
no Coriolis in that, is there? No
Coriolis. No Coriolis in that, but certainly is acceleration.
Have you seen that video? The sniper, the guy took a Barrett 50 cal and shot it straight up, and it landed like 50 feet away from him. It's like, there is no Coriolis there at all. I'm sorry, folks.
So the whole thing is like we are so close to being on the same page on this, but when we, in my opinion, and this is the way I see it, when flat earthers say, well, there's just no such thing as gravity, and it's explained purely by relative density disequilibrium, when there's so much evidence to the contrary to that, first of all, the reaction from the normal person is going to think that's crazy because obviously I drop things, and just saying that it's less dense or more dense doesn't cut it, because as we detailed all these reasons, today, and like I said, it's not even that we are taking this out of the realm of, we're not going into realm of la la land. We're providing absolute, demonstrable, measurable, calculable forces that are causing this to happen. And when I look at it that way, Mitchell, to me, it's something that is undeniable. That's all I'm saying.
I totally get where you're coming from. There's just these barriers that I have to kind of break down in order to kind of come over to that side to say definitively that's what we got.
And that's what we want to do. And one thing, this is what I like about you, Mitchell. You're not sitting here going, Bob, you're a freaking shill. You were here planted, just to dismantle the flat earth community. I mean, I could not believe they were doing that to me. That was absurd.
Yeah, I think, when people get into ad homs, it doesn't help any arguments whatsoever. I want to just deal with the facts, deal with observable reality. It doesn't matter who's presenting it. It doesn't matter where it's come from. It doesn't matter if someone's rehashing it. It's what we can observe, what we can prove, what we can see, and that's why I just want to play this video. I don't think it's got sound on it, but this is bromine next to a vacuum. I don't think it needs sound on it.
That looks like an animation, not a video.
That was an animation.
Okay. What are you doing? Playing NASA here?
No. Where was it? It was somewhere here. Okay, so we got bromine in its own container here. So this is more directed.
Have you ever dripped butane out of a butane filler and watched it drop on the floor? You know, I mean, that's something that I don't know. I don't know why that came out, but again, these are things that we can't see them, you know, what's going on. But yeah, I understand what you're saying. Anyway, continue on.
So yeah, I just want to make the demonstration of the bromine next to the vacuum. So these bits here, that's the vacuum, and this is the bromine expanding into the vacuum because that's the space it has, and that's just what I see is happening around us. When gas gets produced, it expands into the space that it has, and nothing to do with anti-Riley.
The second law of thermodynamics. Nobody is disagreeing with that at all.
Definitely not. No, but do you think?
Well, no, it's part of electricity, though. I mean, electricity dissipates in three ways: in heat, in sound, and in light. So a high pressure system next to a low pressure system, I need to look into this a lot more. I'm not going to claim this, but I would almost guarantee that the high pressure system has a stronger electric field in it.
That's definitely
very slightly.
Yeah.
But yeah, so it's just, that's all much of the, Ken Wheeler says it so beautifully. Mother Nature doesn't have a pocket calculator. She doesn't have a bun in her hair. She doesn't, you know, have her tab writing down all the data. Mother Nature is a hippie chick with bare feet and dreadlocks and hair, flowers in her hair, telling everybody, come on, let's just equal out. That's all she's trying to do, positive to negative. Let's try to get everybody equal. It'll never happen because we're breathing, plants are breathing,
we are in
animals
a
are
constant
breathing.
State of disequilibrium. Absolutely. And we always will be. It's like the juggernaut, you know, it's the thing that until you have a something that causes a disequilibrium to start the machine running, you got nothing. And that very thing that starts this machine running is that downward bias, that downward force.
And I suppose it comes down to the magnitude of these things that we observe happening. So when we see in an unnatural state bromine going into a vacuum, that's induced purely by humans making a vacuum and having bromine in a container, and that disperses really rapidly. But if we have bromine or just another gas in open air, it disperses slowly. Do you think that the electrostatic force still applies in both those situations? Why would there be a different apparent kind of dispersal?
Well, yeah, because in a vacuum you can't have an electrostatic field. There is no electrostatic field. No, in a vacuum.
Yeah,
that's why the ionosphere is important.
That's right, but once you fill it with gas, then you can have an electrostatic. So
it's really that electrostatic field equaling out, going from positive to absolutely nothing. It's just whoosh, fill in that whole space with the electrostatic.
Yeah, like Austin puts it, when you open a soda and it goes, psh, you know, that is that particulate matter that is then able to be ionized. And when you ionize particulate matter, then you have a static field. And
so
that is,
ether,
of course, what we have around us.
Sorry. Would ether come into that? Would ether be would the static?
Well, yeah, that's what I think the ether kind of is. It's the electromagnetic, we'll call it. The magnetic field and the electric field together. That's like what makes everything. If it holds true that, you know, we're made of all these little particles that are all, like we were shown in that incoherent video there. If we're made up of all these little particles that have poles and this and that, then yeah, electricity really controls everything when you break it down.
Yep.
It's really interesting stuff. These are great discussions. In a vacuum chamber, we're not getting rid of ether though, are we? So ether would still be present in a vacuum chamber.
Ether is always present. It is the
so you can't isolate
background medium.
So if there wasn't
things manifest.
Okay. So
yeah, in a video game, it would be space. You know, it's the air, it's the material, it's everything. The animals, it's like what you start off with. It's the base.
And remember,
You know,
the ether has been acknowledged by science for centuries. It is absolutely there. Only Einstein said it didn't exist. Almost every Nobel laureate since him has said that it does exist. The Air Force has redone the Michelson-Morley experiment, said, yep, it's there. We have devices that are based on the existence of the ether, the Sagnac effect, which are the ring laser gyros and the fiber optic gyros, that without the ether, they couldn't work. It's as simple as that. So to deny that the ether is there is unbelievably stupid. It is there. And it's literally, like I said, science has known it for a long time, but the objective of the powers that be are to derail us and put us off in this scientism realm, where bendy space-time and stuff like that. And in order to do that, they have to promote the absurd and discredit the obvious. And that's exactly what they do.
Well, yeah, I mean, the Globers could have an argument if they went with the electricity thing, saying everything, but then they'd run into the problem with the ionosphere, and we just pick them apart right there. So, I mean, that's why they don't even want to touch it, because they know it's not going to go anywhere. They're going to stick with gravity, even though according to MIT, physics, gravity is not what is pushing things down here on Earth. That's the lights in the sky. The moon, the sun, the stars, all that stuff, that's gravity. But here on Earth, where things aren't electrically neutral because we're all inside this electric field, then it's electric forces that, make up and down and all that kind of stuff.
So isn't it interesting, when you have a school like MIT that's teaching stuff like that, which is so counterintuitive to, what the argument from the Globers that we get is. I mean, what Professor what's his name said,
Lewin,
yeah, Professor Lewin said it was absolutely not what the Globers are saying. And that's why I said I think maybe he got into a little bit of trouble there for telling it like it is. And then he put it into the realm of, out there in Narnia, right? Because you say, well, maybe that's true in outer space. But since you're never going to go there, we're never going to know, right?
Well, yeah. Well, he also even said he exposed Maxwell's fourth equation when he was talking. He's like, Maxwell changed Ampere's equation with no proof. There's zero evidence to back up his claims, but it has to be for the world to work the way it does.
Yeah.
For this world to work the way it does, I think he said.
Yeah.
So he's screaming to him as much as he can without coming out and saying it.
Yep. So
this is such a fascinating conversation. This is awesome. We've been going for almost 2.5 hours now. I think we should probably wrap it up. I think we need to do this again. You just want to jam everything in and just get it all covered. It's been awesome talking to you guys. I think kind of for me, what it boils down to with the whole downward bias is, because I've looked into relative density disequilibrium so much for so long, I may have been ignorant to the other side of the discussion that you guys have been putting forward, but it still seems to me that it's all to do with a medium and things in the medium. And the discussion around if there's a downward bias comes down to if there's a cause to equilibrium, I guess, things seeking equilibrium. And
yeah, that's what we're saying. Yeah, that's all we're saying. Everything about relative density equilibrium, it's beautiful. It works. That's how it is. But it needs that little bias. It doesn't have to be a strong one. It just needs that direction for the denser things to, equilibrate towards.
Yes. And up and down are not relative directions. So there you have it, unless you're a baller. But
yeah, thank you so much, Mitchell. That was fun, man.
Thank you, Zach. Yeah, that was great fun. I haven't had this in-depth discussion with anyone about this until now. This is awesome. It's something I have to go back and look at all this evidence. Look at the evidence that I have, and kind of it's down to everyone's individual.
Oh yeah, well yeah. It wasn't easy for me to learn. I know I keep on saying it's so easy to understand, but I need to take that back because I had to learn a new language. It wasn't like I watched a Walter Lewin video and I had it down. I watched the first 8 of his series, which is all about these forces, probably 10 times. you know, at least 10
There's a-
times. And
yeah, there's a lot of
because there is a lot of things you have to learn, you know, just the different terms and this and that and how it actually works, what he's saying. But if you go watch him, he does a great job showing it to you, like physical examples of it actually happening, and then him testing it and showing you, yeah, this one's positive, this one's negative due to induction, things like that. Once you get the basics of these electric forces down, it all falls into place. But yeah, no, density and all that is spot on. I mean, really, it's a beautiful system. It works. Yeah, but we're just saying there needs to be that tilt to tell the denser object in which direction it should go.
Yeah. So Mitchell, I put all the video links and all the stuff that I used in the Skype chat. You can tack them onto the video.
Yeah, I will do that. Yep. I'll have to go through and tack them on. Thank you, both of you, Bob. Thank you, Zach, for being here today. It's been a massive extended edition of Flat Earth School here. I'm hoping a lot of people will get a lot out of this discussion. You have to come to your own conclusions, do your own research. We're merely just putting out demonstrations that we can see, that we can try and prove, and it's up to everyone to do their own research. Just for me at the moment, I'm still skeptical of whether there's a downward bias, but it may change. I have to look into it a bit more.
Yeah, man, you know, just whatever.
We won't call you a shill if you don't believe
it. Yeah, no, you know, you're always.
I'll repay the favor.
Thanks, I appreciate
no shills
that.
here.
Just thank you for listening and giving it an open mind. That's all we ask.
Yeah,
because
that's what it is. Yes.
All right, man.
All right, guys. Well, I'm going to wrap it up. Unless there's anything else you want to put on just quickly.
Nope, that's about it.
Yep. Thank you again, man. This was awesome. Anytime.
Thank you, Bob. Thank you, Zach, for being here on Flat Earth School. And I'm going to end the stream now. It's 2.5 hours. I'm starving.
Okay. Bye-bye. We're out.
See you guys. Thank you for joining us for this very special edition of Friday special guests with Bob Knodel and Zach. Good times for all. If you if you enjoy my work, if you enjoy these discussions, if you want to see more of them, please support me on Patreon. Thank you to all the patrons that have seen this first. They've seen it live. They've been part of the discussion in the chat. And I just want to say to everyone, if you feel like the world turns on you, turn to Flat Earth School. Peace, everyone. I'm Mitchell from Australia, and this is the #1 flat Earth proof. The premise to this starts with the sextant and how we use the sextant in celestial navigation. We look directly through the sextant at the horizon. But if you live on a globe, what horizon are you actually looking at, Globers? Is it the Earth horizon? The water horizon? The horizontal reference plane? The visible horizon? How about the sensible horizon? The geodal horizon? Or the celestial horizon? Well, it's certainly not the geometric horizon, you know, Earth curve. No, that was debunked by the Black Swan over 18 months ago. But now the globe-believing zealots tell us that their horizon is refracted. It's not an actual horizon. So how do we have a tangent to a refracted horizon? When you're viewing a star on a globe, how are we measuring an angle to the horizon if it's refracted? You will never ever get an angle to a refracted horizon. This is a major problem if you think you live on a globe, because celestial navigation would be impossible. So what have you done to keep your religion of a sphere Earth semi-plausible? You've presupposed that that line 90 degrees above your head, the zenith, actually runs to the center of your presupposed spherical Earth. And 90 degrees from that, you've made up a new horizon, the celestial horizon, which you say is a horizontal plane passing through the Earth's center, perpendicular to the zenith. So, after presupposing all these things, you can now use your sextant. But globe believers, realizing that their visual horizon is refracted, can't yet look at the horizon through the sextant. So yet another horizon is needed to be fabricated. They use the bubble level in the sextant to create the artificial horizon, which we are then told is parallel to the celestial horizon, essentially taking away the curvature of the Earth. Because even globe believers know you cannot measure an angle to a curved surface you think's beneath your feet. Look at this. You're pretending you're living on a globe, but in order to measure angles, you need to pretend you're living on a flat plane. This is cognitive dissonance, globers. You can't have it both ways. So now they can actually start and take a measurement from their 0 point of the artificial horizon to the celestial body. Look at what the globe believers are doing. They must treat what they see as flat in order to achieve an angle. But there's one more step, and this is where it all falls apart for the globe. They then have to measure from the artificial horizon a dip angle down to the visual horizon, the only actual horizon that we have. Remember that horizon that you said was Earth curve that is now refracted? Do you all realize now how devastating the Black Swan actually is to the globe? It has taken away your R value, the radius of your globe, and then it took away the curvature of the Earth altogether when it forced you to say that the horizon was refracted. And together with the sextant, it's now taken away your ability to navigate. Since January 1, 2020, the globe has been dead. So now it's time to prove where we actually live. May I present to you the #1 flat Earth proof. Here in reality, we live on a flat plane. And this may be news to people. We also have a flat sky plane above us where the celestial bodies exist. From the vantage point of our flat plane, when viewing the celestial bodies, we perceive their position and movement as a dome. This is purely our perception from this vantage point on our flat plane. It's not actually a dome above the Earth. All celestial bodies rise in the east, move in an apparent semicircular motion above the sky, and set in the west. Now, don't get me wrong, our Earth is measurably, observably, and obviously contained, but it just doesn't have to be a dome shape, or any shape for that matter. But I digress. Looking at this flat celestial plane above our heads, we can see that everything rises in the east, moves across the sky and sets in the west. We just perceive a motion of a dome shape. So let me give you a real-world example of how this works. This is Lake Wollongabula, quite fittingly the breeding ground to black swans, and, I kid you not, located on Black Swan Way. Now, relative to the horizon, if you look up, straight up above your head, 90 degrees to where my drone is sitting, right there, 90 degrees, what will happen when that drone moves straight ahead in its own flat plane? It's not going to change altitude. It's just going to move straight ahead. From my observer point, what's going to happen? The angle is going to change. The drone has not changed altitude at all. It's just changed the distance from where I'm observing it. If it moves again, the angle changes again down to 25 degrees there. As it continues to move away, or if I move away from it, it'll travel towards the horizon, lowering in its angle, and eventually it'll get so far away that the angle will be too small for me to see, and it will appear as if the drone has set. This is all relative to the observer point. This is all apparent. It's not actually lowering. It's just getting too far away and the angle is decreasing. This creates that dome motion and movement that we see in the flat plane of the celestial bodies. Now that we understand that the flat celestial plane above us presents itself as a dome to our perspective point down here on the plane that we exist, we can understand how the celestial navigation actually works. Every star in the flat celestial plane has a position relative to our flat plane where it will be 90 degrees. This is called the geographical position, or the GP, of that star relative to our flat plane here on Earth. When the observer is at the GP of the star, it appears 90 degrees above their head. Celestial navigation works by using a sextant to measure the angle of that known star and using its relative GP, geographical position, to know where you are. And I'll continue to point out that measuring angles to celestial bodies only works if we are on a flat plane. Now, if one observer measures 30 degrees to a star and another observer measures 30 degrees to that same star, we can conclude that they are both on what's called a circle of equal altitude. And this is another killer blow to the globe right here. Everything on that circle of equal altitude is exactly that, equal altitude. No matter where you are on that circle, you're going to measure 30 degrees. And through being able to measure an angle to that star relative to the horizon, everything on that circle, in between that circle, in the area of that circle, is absolutely flat and level. By doing this once with a sextant, you know you are somewhere on that circle of equal altitude. To triangulate your actual position, you need to repeat these steps with other stars. Your position is where all these areas of equal altitude meet. This is how celestial navigation works and has always worked on our flat level plane, using the celestial flat level plane. Let's use this small scale example on Lake Wollongabula. Instead of a drone, we're going to use a star. So if observer A measures an angle to the star, and observer B measures an angle to the star, the same star, both angles are the same, 30 degrees. Knowing the GP of that star, they can conclude that they are on the same circle of equal altitude. Distance between observer A and B and the area inside that circle is all in the circle of equal altitude. It is all flat. It is all the same level. This is the killer blow to the globe. Not only is our world observably and obviously flat, it is measurably flat, as I'm about to show you in this next large-scale example. The rule of thumb with celestial navigation is to use stars over 15 degrees in elevation, because under 15 degrees, we start getting a lot of refraction, as you can see in these moon images. And this is real refraction, where something moves relative to the horizon, not the actual horizon itself being refracted, as anti-flat earthers would like to tell us after seeing the black swan images. So, if an observer was looking at Polaris from 15 degrees latitude, negative 60 degrees longitude, here near Dominica, they would measure 15 degrees to Polaris. And if another observer was on 15 degrees north latitude and 120 degrees longitude, they would also observe an angle to Polaris of 15 degrees, because we know the distance between these 2 points are absolutely flat on the same circle of altitude. We can measure between them and we get 10,375 miles of flat Earth and ocean. And that's been nice to the globe. We can definitely see Polaris on the equator and even sometimes below the equator, which is a much larger distance of flat area, Earth and sea. Let's do this north to south now. If someone was at negative 75 latitude looking at a star with a GP on the equator, we would be on the same area of equal altitude as someone looking at the same star from 75 degrees latitude. Knowing that between these 2 points has to be absolutely flat, let's measure between them. 10,375 miles again, with an area of 84.5 million miles. Absolutely measurably flat. But it doesn't stop there. Look at this map with all the GPs of the navigational stars on them. And the reason why this is the #1 flat Earth proof is because using just one area of equal altitude proves that that large area that we're navigating on is absolutely flat. But by doing this multiple times to create multiple areas of equal altitude, we can literally measure our entire world as flat. Just so you understand the enormity of this proof, we can literally measure our entire world as flat. We are living on a flat Earth. 2020 was the year of the black swan. 2021 is the year of the sextant. There is no more debate. The globe has been killed. The flat Earth has been proven. This is the #1 flat Earth proof.
Wow.